भेज दिया।
सर क्या टाइप सर?
हाँ जी, ज्वाइन कर लेना।
हाँ जी,
I welcome all. Is my voice audible? Dr. Jignesh?
Yes, we can hear you. I can see you very well. Good morning, good evening.
Thank you so much. Thank you so much. So warm welcome to all the participants and all the dignitaries in the inaugural function of our course, which is sponsored by Gyan, Ministry of Education, Government of India. And the title of the course is Multi-Agent and Microgrid Concepts. I extend my warm welcome to the dignitaries here. We have with us the local coordinator of the Gyan Cell, Professor Vijay Jinyani. We also have with us Associate Dean RNC, Dr. Rajiv Agarwal with us. The co-coordinator of this course, Dr. Rohit Bhakar. And our head of the department, Professor Rajiv Tiwari. A very warm welcome to all to this inauguration. Here, I have been given an opportunity by the Ministry of Education and Gyan Cell to conduct this course, and I'm very thankful to them. And I'm also very thankful to Professor Jignesh for accepting our invitation. And he's all ready to deliver the contents to us. This course is very timely course because the power system is going through decentralized monitoring and control. The smart grid and microgrid systems are coming up from all the scenarios of the power system, and microgrid is so much necessary for operation of intermittent and variable renewable sources. It is very much necessary for reliability and efficiency of electrical power grids. And for such microgrids, decentralized monitoring and control plays an imperative role, and multi-agent systems, which is the highlight of this course, is very much necessary to solve the problem that are difficult or impossible for an individual agent to solve. Here in this course is spread over 5 days, and it is going through basics of the multi-agent systems, basics of the smart grid and microgrid to its programming and advanced level. Not taking much of the time, I just want to highlight that we have worked towards popularizing this course throughout India, and we are lucky that we have 80 participants in this course from all the premier institutes of the country, IITs, NITs, and IIITs, and premier private colleges of India. I hope all the participants will have a very grand learning experience in this course and will be benefited for their research and future collaborations with MNIT Jaipur. Here, to give a brief overview for the resource person here, Dr. Jignesh Solanki. He's a faculty member in the Lane Department of Computer Science and Electrical Engineering since 2009. And he has received his PhD from Mississippi State University in 2006. And he is working he's working in Open System International as a senior engineer in Power System Research and Development Department for several years after his PhD. And now he's faculty in the Lane Department of Computer Science and Electrical Engineering. I welcome you all. And now I ask the head of the Electrical Engineering Department, Professor Rajiv Tiwari, to give a brief overview of different research programs which are running in our department and the various research collaborations of our department. Thank you.
Thank you, Dr. Prerna. Yeah. Respected Professor Jignesh Solanki, Line Department of Computer Science and Electrical Engineering, the chief guest of this event, respected Professor Dr. Vijay Jinyani, respected Dr. Rajiv Agarwal, respected Dr. Rohit Bhakar, Dr. Prerna Jain, esteemed faculty members, participants, ladies and gentlemen, a very good afternoon. On the behalf of Department of Electrical Engineering, I welcome you all to this auspicious occasion of inauguration of Gyan Ministry of Education sponsored 5-day course on multi-agent, and microgrid concept. I would also like to greet the various participants from Rajasthan and other states of India. The Electrical Engineering Department is one of the oldest departments of the institute, which was established in the year 1963. Presently, department is offering UG courses in electrical engineering and 3 PG courses of Master of Technology with specialization in power systems, power electronics and drives, and power system management. The department has highly qualified and committed faculty whose expertise is widely distributed in different areas of electrical engineering. The department has current faculty strength of 29. I wish you all will enjoy these 5 days of course with interesting and stimulating discussions and exchange of knowledge. Thank you very much.
Thank you, sir. Thank you very much. We also have with us Professor Vijay Jinyani, Local Coordinator, Gyan Cell. I request him to give us an overview of our activities of Gyan Cell in MNIT Jaipur.
Good morning and good afternoon to all of you. Am I audible?
Yes, sir. Yes.
Yeah. So I extend a very hearty welcome to Dr. Jignesh Solanki from West Virginia University, who is the chief guest of today's function and also the expert speaker of this Gyan course. I also extend a hearty welcome to other dignitaries, Associate Dean, Dr. Agrawal, Head of the Department, Dr. Rajiv Tiwari, Dr. Rohit Bhakar, Dr. Prerna, all the faculty colleagues and all the participants on my personal behalf and on behalf of MNIT Jaipur and also on behalf of the Gyan cell of MNIT Jaipur. As Dr. Prerna mentioned, it's a 5-day course on multi-agent and microgrid concepts. So being the local coordinator of Gyan for the Institute MNIT Jaipur, I would like to take this opportunity to brief you very briefly about the Gyan activities. Gyan is actually an acronym for Global Initiative of Academic Network. And incidentally, Gyan, if you see the word in Hindi, it means knowledge. So it's very rightly named as Gyan scheme. And this scheme is launched by Government of India. It is a very ambitious and visionary scheme of Government of India, Ministry of Education. And the basic idea behind this scheme is to take benefit of the expertise and talent of globally well-known scientists and academicians across the world. And also, it aims at providing opportunity to our own faculty to learn and share their knowledge and teaching skills in emerging areas, and also to provide opportunity to our students to seek knowledge and experience from the reputed international faculty. I am proud to mention here that MNIT Jaipur, being one of the NITs of India, it's a premier institute. It's doing very well as far as the Gyan course is concerned, at least. This Gyan course is one of the 40 courses that have been approved by Ministry of Education to MNIT Jaipur. And by this number 40, the MNIT Jaipur is among the top NITs of India. I think it's the second NIT having maximum number of Gyan courses approved. So for this, we are really thankful to our administration director, sir, who has been a constant motivating force behind this organization of this Gyan scheme. And we are also thankful to our Dean of RNC office, who are providing unconditional support to this scheme. And I congratulate Dr. Prerna and Dr. Rohit Bhakar, who are the course coordinators for this Gyan program, for organizing this event. So I again extend a hearty welcome to all of you, and I hope that this 5-day program will help the students and faculty to gain new knowledge and generate new ideas. Yeah, thank you.
Thank you, sir. Thank you very much. We have with us Associate Dean RNC, Dr. Rajiv Agrawal, and I request him to give us some overview about RNC activities in MNIT.
Yeah, good evening all. I welcome Dr. Jignesh you have joined from distant, and you would be here for more than 5 days and giving your research and I can say academics. You would be delivering all the research which you have undergone in your whole career. It would be benefited for our MNIT, not only MNIT, but all the participants of this GYAN course. MNIT is actually, what I can say is going on in the very good pace, and research ecosystem in MNIT is growing fast. And I can say the innovation, so ministry has mandated India to come up with the global innovation index. So it was initially, it was in ranking of 60, 70. Now ministry wants we should be in the top 25. For that, ministry has actually initiated a one very good scheme for national innovation and startup policy. So previously emphasis was given to publish your paper. Now the emphasis is going to given more on how to commercialize your research. So this is one of the fact. So in MNIT, Jaipur is one of the leading institute in India who has implemented national innovation and startup policy in MNIT Jaipur. And we have more than 5 startups run by faculty members, and many more startups are actually currently in process. So we have very good innovation and incubation center. If this program could be offline, then all the participants could able to avail the facility of that, and they can see what MNIT actually doing in this field. So this is one. Another thing is we have instituted because of this, we are now in band excellent category, the award institute by ministry, that is ARIA, that is for innovation achievement ranking. So we are now band excellent ranking. And I would like to just mention some of our credentials. We have more than 900 research projects which are currently running, and 30 research, 30 journal, 30 projects actually for international category. We have more than 4 projects in the sanctioned by one of the regional academic center of ISRO. So we have, again, this is one of the proud achievement for us. We have a ISRO regional academic center, and we are the, actually I can say, lead institute which has received this ISRO funding. Apart from that, there are a number of projects from in the category of consultancy, in the category of FIST. We are the highest recipient of received funding for infrastructure. We have filed, I think, more than 70 patents filed in last 5 years, and 12 patent has been granted. I can say this program is being organized by one of the strong research group, Professor Bakar and Professor Prerna Jain and our team. And I can say by having their rich research inclination, participant may benefit from expert like Professor Jignesh, and then all the interaction which will happen in next 5 days. So I congratulate and I wish best wishes for this conduction of successful workshop.
Thank you so much, Dr. Rajiv, and it's a pleasure that we are working in such a good RNC environment of MNIT. So now I request the chief guest of the event, Dr. Jignesh Solanki, to just share a few words on this inauguration of the event. For 5 days, he has to speak, of course, for 4 hours every day. But today, some few words for all of us.
Good morning and good afternoon. And I thank MNIT team to coordinate with me to deliver this course. I am also thankful for everyone attending, Dean and Associate Dean and all the team members, Dr. Rohit, Dr. Prerna, for this inauguration ceremony, very well organized. Also, a couple of words that I want to mention to students and my feeling a little bit, if I may say. Our Modi, right, Prime Minister Modi, is doing a lot for the India, and this is again already mentioned. The GYAN is a very well thought scheme, and I am very happy to be part of it. But it is not just me and the organizer. It is about the students, right? Means what you are going to gain, how you are going to use it, right? Are you going to attend it, right? Are you going to attend it fully with your heart and mind present during this 5 days course? Okay, that is the most important part of this one. So looking forward to the interactions with students and sharing my thoughts, my knowledge during this 5-day course. Thank you very much.
Thank you, Dr. Jignesh. Now last, I would ask co-coordinator Dr. Rohit Bhakar to say some few words as a vote of thanks.
First of all, I would like to thank Dr. Jignesh. In fact, I used to travel to US to meet people like you during the Power Engineering Society General Meeting. So we would spend somewhere around 2 to 3 lakh rupees every year to visit that place and meet and interact with researchers, faculty members at that conference. And the value that we could bring out from such events, I see this course an opportunity where all that knowledge that we have to travel so much of distance, visit those universities, possibly can be delivered online, and all our participants from India, they can attend it and gain that knowledge, which is possibly being the research that is being taught at those universities. So thanks a lot for your so much of support. Despite that the course was sanctioned 2 years ago, you have still sustained with us, and we have eventually been able to successfully organize this course. In fact, that means a lot for all of us. Definitely, the ministry, the GYAN course, the GYAN scheme in itself is very good, and we thank the ministry for initiating such programs which can benefit our scholars, understand what research is happening across the world. Definitely, the institute has played a very supporting role. Both the directors, the deans, and the Dean RNC Office, Research and Consultancy Office, which have processed all these things, and we have done many iterations, changing the schedule and all those things, and they have always supported us for these activities. Most importantly, as you suggested, the most important component is the students who are attending this. And without the students, the course is of no meaning. So my thank also goes to those students, those participants who are attending. Faculty. There are a few faculty members as well as a large number of scholars attending that course. So thanks to you, and I'll appreciate if you can dedicatedly attend this course for 5 days. The value at a very low cost, it is supported by the government. The value it can bring to your research is significant, and missing out even a moment of this course means losing out so much of money that we would have to spend to learn those things. So we would request all the participants, all the scholars, to attend as much of the program as possible. Also, thanks to our NKN team for providing us this nice support, in which we do not feel the difference whether Dr. Jignesh is sitting in US and we are sitting in India. It just gives us a feeling that we are just sitting in front of each other. We have got a decent facility by which we can interact with each other. And thanks to all the volunteers, the student volunteers who have supported running this program. So it's all now with the coordinator, Dr. Prerna Jain, putting up so much of effort. So possibly I can take it forward.
Yeah, sure. So thank you, Dr. Rohit Bhakar. And we definitely, all the participants are excited to witness this course. And I'm quite sure and I'm confident that all the participants would have a very good learning experience in this course. So with this, I end the inauguration. And once again, I welcome Dr. Jignesh Solanki for this course. And we will start this course at around 5 time, and it's just 3 minutes. So after 3 minutes, the classes will be started. So I hope, how many participants have joined? 54 participants are already there in this link. So over to Dr. Jignesh Solanki now. And the inauguration is formally ended. Thank you.
Thank you very much. So if you don't mind, can you just turn on the video for maybe a brief moment so I can see everyone's face?
The participants can possibly.
Participants, yeah,
Yeah.
participants, all the students, yeah, that would be nice, yes. Don't worry about the background, okay, so, nice. And if you can change your name so that I can recognize, I see M. Kaur.
हमारा बंद करना स्क्रीनशॉट स्क्रीनशॉट
Mr. Goyal.
स्क्रीनशॉट
Kagan, you are doing good? Okay. Kagan, where are you from?
Right now in Mumbai.
You are in Mumbai. Okay. Where in Mumbai?
So IIT one.
Oh, you are in IIT. Okay. I was in IIT. I was in IIT, a research scholar in control group. I was there in 2002. So good to have you, Gagan. Amit Kumar, how are you? Okay.
Yes, sir.
Okay, that's okay. Some audio problem with Amit Kumar, that's fine. Himani, you are doing good?
Yes, sir, I am fine. How are you?
I am fine, thank you. Thank you, Himani. So Himani, where are you from?
I'm from IIT Jodhpur.
IIT Jodhpur, okay, very nice. Okay, I am not able to see other students, but that should be okay. Okay, very nice. Okay, so let me, before I start, any questions anyone wants to ask, any general questions? Okay, so feel free to send a text message or raise your hand. I don't know whether I will be able to see your hand or not, but just speak out, unmute and speak out kindly. And as far as it is related to the course, I think I welcome all the questions, all the curiosities, and I will share what I know, okay, for sure. Okay, so with that, I think let me share my screen, okay, presentation. Okay, I hope you can hear me, right?
You are audible, Dr. Jignesh, comfortably audible.
Okay.
I think the screen needs to be made full screen.
Okay. Okay. You think you can see me? You can see my screen?
Yeah.
Okay. Okay. I will just keep it like this. Give me 1 second. Okay, this is good.
Even this is good.
Okay. Okay, so I think all has been said for the GYAN program. Okay, it's a very important part. It's brain drain, basically, you can call it. And I think most of the Indian origin faculty member would love to share their knowledge and make India great. Okay. Outline is already shared by Dr. Prerna and Dr. Rohita, and we will be closely following that. Okay, we will be closely following that. So in day one, mostly we'll be talking about the general power system, and then introduction to agents, probably, and then applications to power systems. A lot needs to be talked about. Okay, so I'm not going to day 2, day 3, day 4, and day 5. Okay, so we'll go as we progress. So today, this is my plan. Okay, so overview of the power system, what is happening here in the United States, and in general power system, the overview of software automations, buzzword smart grid, right? For last 10 years, what is happening. And then the need of the decentralized control, very well said by Dr. Prerna, very important part and very well needed with new resources coming in. So introduction to agents, we'll talk about, and the past applications, how agent has been used in the research actually, right? And showcase that what can be done, what are the capabilities these agents have, or decentralized control basically, okay? Okay, so I will start with this map, and probably no one likes to see the map divided, right? But this is our map for the power grid, okay? And then so this is US and Canada. So in the top side, we have the Canada here, and then rest is US, okay? So US has basically we call it NERC interconnections, North American Electricity Reliability Council, North American Electricity Reliability Council. What is his job? To promote reliability and adequacy in transmission systems, okay? NERC develops and enforces reliability standards. So we have standards 99.99 percentage reliability, okay? That means if you count it, it comes out to be a couple of minutes that you can have the outage in the United States, okay? But if really, sometimes it happens that some weather-dependent incidents can happen, and you can have a outage for longer durations, and you might have heard about a Texas outage. So we'll talk about it as we progress. But this one we have on the left side, Western interconnections, we call it, okay? This is Southern interconnection. Somehow it's not been called, but southern part of the United States, but it is called ERCOT, okay? Interconnections. So this is mostly Texas. And then this one is Eastern interconnections, okay? We have in Eastern interconnections, the grid is managed by, one is MRO, we call it Midwest Reliability Organizations, okay? And then we have Northeast Power Coordinated Council. Then we have Southwest Power Pool, okay? So that is multiple states together. So this entity is seeing the electricity reliability on multiple states. And then this entity has been overseen by the NERC, okay? Reliability first, RFC, okay? And then we have this SERC, Southeastern Reliability Corporation, and Texas Reliability Corporation. So then next question comes out, why we have this divided map, okay? So did I lost you guys? Can you hear me?
Yes, sir, you are audible, sir.
Yes,
okay.
sir, we can.
Okay, thank you, thank you. Okay, understood. Okay, so host has stopped the video, so that is why I lost my screen, but that should be okay. So okay, so what I was saying is that why this map is divided. So that Western and ERCOT and Eastern interconnections in the United States are connected by DC line. So that WECC, right? That is everything that we have is AC interconnection. Eastern interconnections are AC interconnections, and ERCOT is also AC. But all these three are connected by DC lines. Okay. Why DC line? So when you have a research says that when you have more than 400 kilometers or 400 miles of line, you can get the benefits, economical benefits to have the electrical, to have the DC connections. So that is why. So then WECC and MRO has a DC connections. Similarly for Quebec interconnection, like Canada, also they are connected by DC lines. So everything is DC here. So ideally, WECC, Eastern interconnections, and ERCOT interconnection and Quebec, they can operate at different frequency, ideally, a different frequency, 50 hertz, 55 hertz, 60 hertz, whatever. But here, I think we have a 60 hertz frequency in the United States or North America, I would call it. Little bit deeper view of those interconnections. And now you can see those DC tie lines. If you can see my cursor, that is triangle arranged upside down, both triangle, that is a DC interconnections. Okay, so these all are connected DC interconnection. This is Eastern. Additionally, you also have some DC interconnections in the Western Electricity Council as well. Similarly, for the ERCOT, we have these DC connections, and if you can see on the top, the Canada is also connected by the DC tie lines. Okay. Now you can see that it's already the electric grid is very complex, right? You can see thousands of lines and so many utilities, electric utilities managing this electric grid. Okay, the smaller the dots you see, the smaller the utility, and larger the dot you see, the larger the utility. It goes from anywhere from 400 customers to 10 million customers from the electric utility perspective. Okay, and then we have here this one. I think it is New York. Okay, but I may be wrong. Okay, but just to give you the emphasis that when you are working as a power engineer, anywhere you are working as a power, even you are playing a small role as a power engineer, you are affecting the lives of so many people, right? So your action can benefit the electric grid, right? Benefits electric grid reliability, benefits the reducing the efficiency and all parts of power systems, right? So it's very important to understand that what we do as a power engineer, it is maintaining this electric grid, building the electric grid. Okay, and now a little bit larger view of the United States power grid. Okay, here you can see again it's very complex, lot of transmission line, distribution line, so many generators. It's not seen here, but at least you can see that very complex our electric grid. Okay. And I could not find better picture for our India. Okay, but this is a nightly picture. I had to work hard to find a good picture, but this is the best I could find. Okay, so this is our India. Okay, so showcasing the electric in the night. Okay, so it's not brighter view. I couldn't find it. Okay, on this one. Midwest ISO. And so this one is Midwest ISO. That means this part, green part we are talking about. In this green part of the United States. Okay, what we have. Okay, so in that part we have 15 states. Okay, so we call it Midwest ISO Independent System Operator. Okay, its goal is to provide the electricity. Okay, reliably and provide a market. Okay, unbiased market basically to sell electricity, consume electricity, buy electricity. Okay, and oversees that everything is running smooth. Okay, that's the goal of this entity. Is called Independent System Operator. Okay, so here we have 15 states. Okay, and also this is connected to one of the Canadian provinces. The control center for Midwest ISO we have is in St. Paul, Minnesota, and then Caramel, India. Okay. Generation capacity 186 gigawatt. Okay. Historic peak that I could find that was given in 2011 is 127 gigawatt, maybe 10% increase by now, or maybe a little bit more. Okay, 10 or 20%. In this 15 state, how many miles? 65,000 miles of transmission lines. Okay, and varying voltages from 500,000 to 69,000 volts. We also have 765,000 volts line. India also has that line. So that 65 is about 90 or 100. You can say 100,000 means 1 lakh kilometer transmission line in that one. See this 1 lakh kilometer, and then the generation capacity. We have 295 means 2,95,000 SCADA points. SCADA stands for supervisory control and data acquisition, okay, SCADA data points. And in that one, we have about 6,700 generating stations. SCADA data points, you get data points in 3 seconds, 5 seconds interval. You pull the data 3 seconds, 2 to 5 seconds, I would say. Okay. Annual billing, right? It's very important, right? We are saying that we are generating this much, but we are not getting the billing, then something is wrong, right? So this is 598 terawatt hours annual billing from this 15 states. Okay, the cost of this one is 80 megawatt hour. Okay, $80 per megawatt. It's about $6,000, 6,000 rupees, right? And that is recent data, that one in March 2020. So this in 52 states, 15 states, this entity is supporting 42 million people. Okay, and that is 4 crore and 20 lakhs, if I'm right, 4 crore and 20 lakhs. They have 471 market participants. Okay, what is participants? We'll talk about it. What is market participants in the next couple of slides. And they have 2,000 plus pricing nodes. Again, we'll talk about pricing nodes. 22 billion annual gross market charges. Okay, to run this one, basically 22 billion annual gross market. Versus, if you understand this one, okay, so we are just talking about 15 states, 4 crore people. Okay, 4 crore. Here in India, we have a demand of 200 gigawatt. You can kind of say this almost equal to this one, right? Almost equal to this one. So, and that was reported in July 2021. Okay, and the cost is definitely much cheaper. Okay, but this is for all of us, like 130 crore people, right? So it's daunting, I would say, daunting for us. And as a power engineer, we have to work hard so that more people get electricity, more people can afford it, right? So this is just 4 crore versus 100 crore, that's consumption. So it's very important. Your role is very, very important as a power engineer, okay? So when we say that United States, very good reliability, very good standard, very well managed, right? But we still have disturbances, and this is the report of kind of showcasing the major disturbances in the United States. Okay, that is from 2000, right? That is 30. Here we have 30 incidences, and then up to 2020 we have 383 incidents, right? That's again alarming, right? So what is happening? That why incidences are increasing? We have to look into it, right? But we need this data before we can look into it, what is happening. So there is an entity in the government, federal government, that is seeing this, okay, what is happening. Okay, my 2 cents on this one is basically lot of integrations of renewables, okay, a lot of integrations of renewables and different vendors, and that is creating this one, these incidences. Okay, overview of power grid components. So let's increase this one a little bit, okay? So in bulk power generations, we have hydro, that is must, right? Nuclear must, coal power plant must, okay? Then we have biomass, geothermal, pump storage, and definitely a lot of wind are being integrated into the United States, and solar power plant, okay? So this is, it's a grid scale, okay? It's not like our home wind and solar. So solar basically, right? A lot of things, a lot of investment is going on in India for solar power plant, rooftop. Every house should have a solar power plant because we have very good solar sun coming in here. Where I live, we don't have a solar. I mean, we don't get almost 2 months, very couple of hours sunlight we get 2 months. Okay, it's extremely cold, January and February. So when this power plant is generating the electricity, it is sending that electricity to the transmission line, okay? And that transmission line has substations, okay, market in that one. Also here also we have in the generation market, if you can see this one, Okay. And then I know Dr. Rohit and Dr. Prerna mentioned that some of the participants that we have are working on the power market side. So it's very important. Market is very, very important. And when you have a market, you can have a economical electricity prices, right? So if you don't have market, then someone is going to govern the price. Okay. So in generation also you have operations, right? So how to operate, when to operate, how to optimize, all these things are happening here. Okay. As far as it is owned by one of the companies, if we have several owners, that every owner will have their own management or their own operations of that electric generations. Okay. So this generation now sending power to the transmission lines. Okay. And various controls, very important is the sag, and we call it the line sags, right? Voltage sag is happening. Okay. So you have to be careful when we are designing these transmission lines. So, and we have to observe what is happening all the time. And then this transmission lines send the power to the distribution line. So we have several, we'll talk about it in next couple of slides, several transmission companies that is overseeing this transmission line operation, overseeing the power flow. Are we overloading the transmission line? Are we underloading the transmission? How we can get the best maximum output from this transmission line infrastructure that we have. Okay. So now from generation to distributions, okay, that is a one-way power flow, right? And then we will have a two-way power flow when we have renewables. So in distributions, in the distribution side, okay. In the distribution side, okay. Also, we have substations, we have capacitor banks, sectionalizers, distributed generators, right? Photovoltaic, wind, and PHEVs, and customer basically, right? Us consuming the power. So from generation to transmission to distribution. In distribution also, not fully marketed as of yet, but we still have market in distribution sites. Okay, so we have operations of the distribution, market of the distribution. In California, there were a couple of distribution control center. I think if I am remembering, two distribution control center came in. It's about $45 million investment. You can very well Google it or YouTube it. Distribution center, so distribution grid model. And you can in real time you get the data from these smart meters and manage the grid or overseeing the grid. You can do better outage management and those kind of things. So distribution controls are popping up in the United States now. Okay. And then after that, once we have the distribution, then we have the customers, right? So and all kinds of customers, and every single one needs the electricity, right? And reliably 24/7. Okay. Without that, in modern days, we cannot live without it, right? Probably one day we can live without the electricity, but no more than that, right? Industries, then buildings, right? Anywhere you think about multi-dwelling, the normal appliances in the house, every single equipment needs electricity, okay, that runs by the electricity. Where you have a motor, okay, some kind of motor, you need electricity, right? Whether it is elevator, or whether it is a dishwasher, or whether it is a washer and dryer, right? So you need electricity, basically. So general overview of this power grid, okay, smart grid we call it. And when we talk about smart grid, we will talk about a two-way power flow, okay. Okay, I think that's good. Okay, I think Dr. Prerna, if you can keep that window open, that would be good. Somehow I'm feeling alone here when I don't see the participants window. Okay. Restructure. So restructuring status, right? What is restructuring? Restructuring means when earlier, when our electric utility or electric grid was established, we have generation, transmission, and distribution owned by just one entity, right? One entity, and that was the price and everything is governed by that entity. So in about 1995, in the United States, declared that we have to decentralize, means restructure the power grid, so that not a single entity owns all the assets of the power grid. Okay, and this is the status. So that means they sold generation to generation company, transmission, then it becomes transmission company, distribution, and then it becomes distribution company. Okay, so all these assets are sold. Okay, and that's the status of that one. And when you see 0.93, that means 93% of the assets has been sold in that particular states. Okay, so that different entities, and each entity goal is to maximize the profit. Okay, but when you have multiple participants, multiple people, multiple companies are coming into this market, automatically the cost will go down or the efficiency will increase. So that is the benefit of doing the restructuring in the power grid. And if you see here on the right side map, different colors. Okay, so wherever you see the color one, those generally states are more active on the restructuring. In the gray part, where you see still more majority of these equipments or majority of the assets of the power grid are still owned by single entity. Okay, restructuring. Now US generation mix. Okay, US generation mix, we have renewables, definitely nuclear. I think nuclear is gonna be very important, very important down the road. Power coming from the nuclear power plant. Okay, coal 19%. In 2009, when I started teaching in the West Virginia University, at that time the coal consumption was 49%. So in 2009, the coal consumption in the United States for the power operation or power grid generation, okay, that was 49%, and it's almost like 10-12 years they reduced to 19. And at the same time they are increasing the renewables. The goal is to increase 99%. Okay, but not immediate goal. I think 20, 50, 30% renewables or 40% renewables. Here we are putting renewables 20%, but hydro was already there 7%. Okay, so renewables means wind and solar for general public, right? But all these are renewables if you think about it, biomass and geothermal. And so solar in last couple of years, solar and wind, we have like 10% or 11% penetration into the grid. So that is still quite a lot, right? Think about here, and this is the 2020 data, electricity consumption from the Department of Energy, 102 terawatt hours of consumption, 102 terawatt hour. Okay, and then 2019 was 106 terawatt hours consumption. Okay, just to see that the COVID affected. Okay, 4 terawatt, I would say. And then we have industry, right? Out of this, 25% is taken by the industries. Okay, and then residential, 34% customers that we have, 34% consumptions. Okay, and then we have commercial 20%, and system losses 10%. Okay, that is, I think I am seeing first time that they are reporting 10%. That's quite a big losses. Okay, 20% losses are quite big losses in this one. Okay, but remember we have millions of transmission lines. Okay, and millions of distributions line. And when we transfer the power, there has to be losses. Okay, there has to be losses. I square R losses that we consider. Actually, I square X also are losses, but we don't pay attention to that one. So it's very important. Okay, commercial, right? 20% consumptions. Okay, and then 9% is consumed by the utility, right? to run this one, basically manage the grid, manage the power plant on that. Little bit about rates. You can compare these rates compared to India. Okay, there is no comparison, but just understand, right? Means in Hawaii is an island. Now I think a lot of renewable penetration in Hawaii. 32%, 32 cents per kilowatt hour. Okay, 32 cents probably is 1/3 of sorry, that is, let's say 90. Okay, so that is 30, about 30 rupees per kilowatt hour. Okay, about 30 rupees if I am calculating right. Okay, and where I am in West Virginia, okay, West Virginia, we have about 12 cents per kilowatt. Washington, where you have Facebook and Microsoft and Amazon, okay, all big companies, that's the state's Washington, okay, and they have like 10 cents per kilowatt hour rate, electricity rates. So when you have this large grid, right, when we talk about this one, so you need to manage this grid, okay, and I think that was in 1970 blackout that federal government or the management of the power grid people, okay, they declare that we need real-time monitoring of the grid. That was in 1970, okay, and after that lot of development happened, okay, and we got energy management system. Sorry, I'm looking at okay, so that is managing the grid in real time, basically energy management system. Some call it software management, okay, software automation. So that is this is energy management system. And I think Dr. Prerna mentioned that I was in a company called Open Systems International. I worked for a couple of years there. That was purely software management, okay, software automation. So, and we used to write algorithms in C programming, okay. And I was part of this energy management system, distribution management system, generation management system, and there were other software as well. So I'm talking about the experiences that we got during that energy management system. Okay. So in energy management system, we have generation management system, transmission grid, okay, energy management system, and distribution grid energy management system. Okay. In generation management system, we have economic dispatch. You might have learned that one, right? If not, then probably if you are doing MS, Masters or PhD, you will learn what is economic dispatch. Economic dispatch is basically when you have a number of generating plants, how you can operate, what should be the operating point and at a minimum cost. Okay, so what should be the power output of that generator at a minimum cost. Okay, that's the economic dispatch. When you have unit commitment, when you have a unit commitment is what is unit commitment, right? So generally day ahead unit commitment or week ahead unit commitment, 15 minutes unit commitment interval or 1 hour interval. So you plan your generator asset based on the load prediction. What generator should be on, what generator should be off. Okay, that is unit commitment. And unit commitment and economic dispatch are tied together. Okay, and then automatic generation control. Okay, so dynamic frequency management basically is done by this automatic generation control. Okay, so how much based on the predefined sharing of the generator on the load fluctuations. Okay, how much each generator has to come produce, okay, to contribute to that change. Okay, that is coming from this automatic generation control. Okay, short-term load forecasting. Then we have transaction management, market operations. Okay, there are other modules are there in generation management system. Very well has been used is this short-term load forecasting, generally neural network. When I was there we had about 7 to 10% error in our load forecasting Generally, whenever utility uses this tool, they see 7%, 10%, sometimes 20% also. But general range, 7 to 10%, and probably it might have increased by now. Okay, a lot of things are happening with artificial intelligence. Okay, so and a lot of additions probably is happening in this generation management system as well. So unit commitment, minimizing operating costs while satisfying a projected demand under system operating conditions, right? And then multiple algorithms based on the requirement and complexity of the application. So now this one is kind of a screenshot. If you see, let's see if we can bring to front. So this is a screenshot for the unit commitment program, and you can see you can select different algorithms here on the top. Okay, and then constraint, whether you have a crew constraint, spinning reserve constraint. Probably we'll talk about it. What is spinning reserve is? Market constraint, dispatch constraint, transmission line constraint. Okay, a lot of constraints. And then period, you can have a reserve period, 30 minutes, 1 hour, 15 minutes, how you want to operate basically your set of generators. Okay, and what are the constraints that you have. Basically, you can configure here and then run that. And I remember we had from Jamaica, we had a request. We had a what do you call? They had I think 12 generators or 15 generators. Okay, and they wanted to run this unit commitment in 15-minute basis. Okay, it took about 20 minutes for 1 week, 15 minutes at that time we are talking about. Okay, so 20 minutes again is a lot of time to figure out just 12 units. Okay, but if you think about 12 units is 2 to the power 12 combinations every single instant of time, right? You have to figure out 2 to the power 12 combination is just beyond the calculation capabilities. Okay, and still getting it in 20 minutes, that's kind of quite an achievement. Upper window are always on, and below the lower window are always on. Okay, so that's the window dynamic programming. So, right, requested by the utility because they are operating, they know what they are looking for, managing their generators. Okay. Unit commitment output is used to evaluate interchange scheduling, maintenance scheduling, load management, and other system characteristics. Okay. Unit commitment has several modules. Okay, so unit commitment has generally we have to run economic dispatch to match the demand, right? So every hour or every 15 minutes, if your demand is known, you want to match it, right? We want to generate that much generation. Okay, every 15 minutes, 30 minutes, or 1 hour interval. So what is the economic dispatch objective? Minimize the costs and meeting the load demand. Okay. Then we have fixed dispatch, provides an option to reallocate the economic parameters without changing unit commitments schedule. Okay. Then we have modified dispatch, analogous to fixed dispatch with operator inputs allowed. Okay. A reallocation of commitment schedule. Okay, because once you have done it, you run your unit commitment for 20 minutes, and as a user, you know your unit, you say, whatever you gave me, I think I want to change this to units, okay, out of this, okay, or 2 hours out of this, what you gave me the answer. Okay, so then how we can reallocate? That's called modified dispatch, basically. Turning unit on, okay, and turning unit off. Okay, specifying a set point for the generator. Okay, so now program, because economic dispatch calculated what should be the generation at that particular hour from one particular unit. Okay, let's say if that unit has 0 to 100 megawatt output. Okay, and then we got that particular hour that generator output is 50 megawatt. Okay, so now we want to change 50 to 60 megawatt because we know that we can run that one. Okay, we have the fuel and whatever the reason behind it. Okay, so it is just a program, and user wants to evaluate if I make this change, what other things are going to change. Okay, so they don't have to calculate, and just impossible to do this, right, by hand calculation. But once you work 10 years, you know exactly what is the economics for your generators. Okay, so accounting for unit duration. Okay, what is duration? Duration means kind of derating the unit, right? Applying the limits of the unit commitment generators. So we have a ramp up and ramp down limits. Okay, so accounting for unit durations are also included into the modified dispatch. Transactions evaluations. Okay, cost analysis for scheduling hourly energy transactions. Okay, it's also available. In that module, we have mode A, mode B. Because a fixed commitment is used, the user must input a transaction data for each hour into the program. Okay, that is user defined basically. Mode B, this mode is identical to mode A, with the exception that instead of using a fixed commitment, it uses the UC program, means unit commitment program, to determine the commitment of units that are based on the additional transaction data. Okay. Responsive reserve, very, very important. And I think it is required by this NERC and FERC, okay, for maintaining the reliability. So responsive reserve means if your unit is on, and if there is an incidence, either a fault or large load comes in, these are the units that is going to provide the response to that change, basically. Okay, that change. And so very important responsive. Minimum of 20% of high limit and difference between unit's current generation and the high limit. Okay, that's the responsive reserve. But minimum, if you have 100 megawatt, this generator has 20% responsive reserve, means reserve for changing. Okay, most generation cannot afford that, right? 20%. Think about that one. We can't afford it to just keep the unit ideal and not taking power output from that one. But that's the requirement, okay, so that we can have the reliable electricity. That means we have to build more generating plants to get the reliability that we want from the power grid. Okay, so when we talk about this one, why we are talking, right? We are talking about multi-agent systems. Why we are talking? To understand what has been done. Okay, so all these applications. Now think about unit commitment, right? When we talk about 2 to the power 12 combination. Now think about as an agent, we'll talk about distributed control, Dr. Prerna mentioned, right? So how we can use these agents to speed up this process, right? That is also a good PhD project, right? Or MS project, or maybe if you are working in a company doing a distributed unit commitment. I think that's a very good contribution. Going from 20 minutes to 5 minutes, or maybe 1 minute, right? Calculations. And I think it can be done. Okay, if you put efforts, it can be done. Energy management system. Applications. So this one is the most widely used, basically. So you have generation management, energy management, and distribution management. Now there are distribution control center popping up, but this one is 10 years back. This one is the most popular, and I should not say 10 years back. When we talk about that, we have smart grid. United States has smart grid. Okay, so it's 5 or 7% of the grid that is that has this kind of capability in the substation level. But in transmission level, that is 100%. It's 100% transmission are have a real-time monitoring. You can see this one of the control center here. So you can see, you can control any line, you can control any transformer, you can control any FX devices, any capacitor bank, just sitting here in this control center remotely. So, and I think every utility has this kind of applications in their control center. Okay, every utility. And then when we talk about every utility means slide 18. So that is, we are talking about here. So every large utility will have this kind of control center for managing their system. Okay, energy management system. Okay, what is the heart of this energy management system? Earlier, it was state estimator, okay, because we did not have measurements, every line that we want to measure, and state estimator as least square methods, right? You can basically find out what are the other measurements. If if uh, if your electrical grid is observable, okay, you are master student, probably you will learn these algorithms, okay, state estimator. But now most of these transmission grids are real-time monitored, so you probably don't need a state estimator, at least in the United States I am talking about, okay? But you can use it for other purposes on this one. Then power flow, okay? Power flow, I think every power engineer should know power flow, right? All the methods, fast decouple, and Newton Raphson's and all other methods, okay? So no, that is the heart of this on this one. So whenever there are instances where we have to combine state estimation and power flow, okay, where we couldn't get the measurements. So what is the best we can come out, okay, with knowing the nominal load, nominal information of the assets that we have, or the generations or loads that we have. So combining this, we can get at least better idea what is happening with the grid. Okay, this one again is optimal power flow, still challenging in the grid. What is optimal power flow? Okay, so let's say at one time instance, your grid is running generation, transmission, and distribution or load basically. Okay, so we want to take that data and come up with the optimal power flow, means apply these optimal power flow algorithms, okay, and change the set points of the generators, okay, such that we will have many objectives in that one. But let's say optimal power flow has an objective of minimizing the losses, okay. So to minimize the losses, what are the set points that we have to do in the generations, right? So that we get the minimum losses. So very important, optimal power flow. Okay, and why I say it's challenging, because when you get the results, by the time you have the new set points, right? And now you ran the optimal power flow after, because it takes time. Okay, and if you have a larger grid, it takes time, at least I would say not more than minute or two, but it takes time. Okay, it's not instantaneous. You don't get results on instantaneous. So that is again a PhD topic, optimal power flow. Okay, how we can kind of think of as a predictive optimal power flow, right? If we can do that, then we can solve many unsolved problems on the power grid, because whenever we are coming up with the optimal power flow result, by the time our grid has already changed right now. Okay, so it's very important, optimal power flow. If you are working, if you are learning, that's put efforts to learn that one. Contingency analysis, all the time it is used. What is contingency analysis? Is that if you know that tornado is coming, okay, or lot of rain is coming, or anything that is a weather related disaster, okay, is going to happen, then you can run what if scenario. What if these two lines will go up? What if these two generators will go out? What if this entire portion of this grid goes out of the grid because affected by this weather? Okay, those kind of analysis we can do. And then once you have the results of the analysis, then you can run optimal power flow, okay, and see how you can manage the grid. Okay, so it is still doable. Short circuit analysis, very important, right? I think many of you have learned in your bachelor degree, right? What is short circuit analysis? How we can figure out the maximum current, right? Whenever you have a fault, right? Probably I should ask, what is the worst fault? Line to ground, double line to ground, three-phase to ground, okay? And I expect that everyone should be able to tell me that three-phase to ground fault is the worst fault that we can have. And if I ask you, what is the worst location for the fault? Okay, the line side, generation side, load side, okay? So you should be able to tell yourself if you are a power engineer, at least if you have done master, BS, or at least in this probably the masters, okay? You should be able to tell me the worst location at the terminal. If you do the three-phase to ground fault, that is the worst you can do for your generators, okay? But now there are a lot of protections devices, so we won't be able to damage it. So that's a good thing. And then this is the most wanted basically tool, operator training simulator, okay? So what this operator training simulator does is that you take the snapshots of this grid anytime that you want to do what if, okay? You take the snapshot and then run what if scenario on that one, okay? And then implement it back on that one. So very a good tool, okay? And also it gives you a newcomer that how you can black start, how you can control any devices sitting at your desk, okay? So very good tool. It has all the modules, state estimator, everything, but it's offline basically, right? You are not disturbing the grid in real time. You don't want to turn on and turn off, right? A load, or turn on and turn off the generators to run, right? We can't do that. So that's energy management system, and lot can be done. Once you have this one, agents are the one that can help us. All this contingency analysis, again, big problem. It takes a lot of times, okay? When we say that n-1 contingency, if you might have heard that word, right? n-1 means if you have n component in the grid, right? If one component is out, how the grid will look like, okay? So if you have 1,000 components, that means you have to run 1,000 times one component out. 1,000 times, that means you have to run that power flow 1,000 times. If n-2, I think probably now computers are advancing, probably we should be able to do n-2 and n-3. That means two component, any two components out. So many permutation and combination, just think about it, right? So lot can be achieved by this distributed control with the agents, okay? Faster, quicker response, not optimal, but faster response we can get it. So very important to understand this, okay? Okay, so I will pause here. I think I am talking too much and I will see if you have any questions. You can write me in the chat.
Hello.
Yes.
Sir, can you please repeat like this EMS application context with this operator training simulator and state estimator?
Okay, so what is operator training simulator, right? So before, let's say if I got a job as a control room operator here, right? And then my job is to see that all the voltages are good, is any lines are overloaded or not, right? And any generators are violating any voltages. So how I can learn that one on that system, right? So that's the training simulator. So anytime in this operator room, lives, what is happening live, right? Means all the measurements on the lines, all the modeling parameters. So light, you just click a button, okay, and you get the snapshot of that system, a time snapshot. What was the generator? What was the line flows? What was the load? Okay, and once you have this one, now we want to say, okay, probably this line I'm seeing that there is a violation. Okay, what if I run the optimal power flow on that? Okay, and remove the violations. So now you run the optimal power flow. You say this is the line overload, means already know that optimal power flow, that is the line is overloaded. Okay, and you get the results. Okay, and you say that these are the outputs. Okay, again, that probably might have changed by the time you get the results. But if you are still seeing, probably there is a good chance that you can change that generator values, okay, and remove the violations, okay, and then you have a larger confidence for doing that because of this operator training simulator. So you can run all the state estimates. So you can also run the state estimator. What if my two measurements, let's say I am running the state estimator, okay, what is state estimator? Estimating voltage, current, and power and other parameters, okay, generally voltage basically, okay, voltage, magnitude and voltage angles, okay. So what if I don't have these two measurements, something happened to my volt potential transformer and current transformer, and I am not getting these two measurements, okay, how the results will look like, so that you can use this operator training simulator to do that kind of analysis, that okay, whether I will still be able to see my grid 100% is still observable, or when I have these two key measurement goes out, I have an electrical island that is not observable. So a lot of things you can do with this operator training. Okay.
So, sir, it's a type like we can do contingency analysis on this operator training simulator.
You can do contingency analysis on the operator simulator, yes. And you can use this operator training simulator to train your control engineers basically, as if you are kind of generally when we were giving training for this software, we were testing black starts, how you are going to start. Let's say grid is off, everything is off. Okay. Now how you are going to start this, your grid. Okay. So you can do black start capabilities, which generator you should start first, which generator you should start next. So those kind of analysis you can do with this, means you can train yourself with this operator training simulator.
So you mean they are the various softwares like on which we work, like RSCAD, etc. Am I right? Or
Yeah,
do
it
you
is a
mean
software,
something
right?
else?
It has all the algorithms, state estimation, power flow, right? Optimal power flow, contingency analysis, all the algorithms that is there. Uh, but it is giving you, you can do it on the real grid as if you are doing on the real grid. Does it make sense?
Yes. Yes,
Okay.
sir. I think it means the same like RTDS. With RTDS, we work on this RSCAD software.
Yeah, RTDS is a little bit different, but yes, you can say it like RTDS. Okay. In RTDS, we have RTDS in our university, and next thing that we are doing is integrating. Right now, we are integrating all the relays to the RTDS. So a lot can be done with the RTDS. You can do hardware in the loop simulations. I think the next thing that is needed is testing all the manufacturers' controller for renewable, means solar power, solar panels, right? Every manufacturer has their own controllers, okay, and they are fighting in the grid. A very small level, means from the transmission perspective you won't see it, but on the distribution perspective you will see it. And then in our houses we are losing our bulbs all the time, okay, because of this controller. That's my 2 cents on that one. Okay, any other questions for me? Okay, Rahul mentioned here is that residential consumption is less compared to industrial in the United States concept. Okay. So let's maybe one more question I can take.
Hello, sir, can you hear me?
Yes, I can hear you.
My question is, sir, like with the coming of the smart devices which we talk about, like today, we read in research like IoTs are the incoming technologies, and now IoT smart devices will come. So how do you think like this uh, what they say like blockchain enabled grids or distributed grids would be in the future?
Okay.
Like P2P transaction kind of model.
Okay. So I honestly don't know. Okay. But if I have to put the best guesstimate on that one, is we are still far from doing that. Means is think about you have a generation company, you have a transmission company, you have a distribution company, and now we have consumers. Okay. So when we have to buy something in the market, just vegetables, right? So we go out and buy the vegetables, right? And we don't care where it is coming from, right? We don't care who is growing it, who is transporting it, but we just consume it, right? It's very similar to that concept. Okay. So when we say that pay to pay, so now when we say that we consume this much power in one day, now we are just going to pay because we consume it, right? We don't care whether it is coming, where it is coming from or not, but we consume the power and we are ready to pay. Okay. So we are paying. So now we have to build the infrastructure such that this payment will go to the right person, because once generation company send power to the transmission line, then is all Ohm's law, basically, right? Means there is no such thing as vegetables in that one. So the power is going to flow through the electric grid based on the impedance of the transmission line, right? So generation company is generating and we are consuming, but power is going to flow through the transmission line based on the impedance. So then we have to come up with compensating this generator company, compensating transmission company in a right manner. So if we have that kind of market, and probably blockchain may be a good candidate to achieve that. Okay, but I don't know the answer. But good question.
Thank you, sir. Thank you. I got some, at least some.
Okay. Sure. Okay. Any other question? Okay. So I think one last one. I think I see someone wrote it here, and then we'll go back. Distributed. Gagan writes here that we have distributed control. Distributed control can provide faster response, but not optimal. So will it be useful for doing economic dispatch for a large system where optimal solution is important? Okay, so see that optimal and distributed, right? So suboptimal is all about timing, right? So whether you are able to wait to put your findings into action, or whether your system can sustain and maybe occur losses, okay, larger losses compared to suboptimal solution. So it depends on the system, okay, and both solutions are valid solutions, right? You can wait and apply the best optimal solutions doing the traditional economic dispatch, or you can do the distributed dispatch, okay, and then work with the suboptimal results on that one. Okay, so it depends on how you want to do it. Okay, but I would say that most likely distributed control should be much faster. Okay, and you can apply it right, and then you don't need to wait out for getting your results. Okay, then I think we can talk a little bit more. Okay. So this one is distribution. Now you can see that our grid is complex, right? Now we have three phases, three lines, and all phases are different flows compared to transmission, right? In three phases in transmission, we have generally balanced flows, okay, generally speaking, and then generally the voltages are much balanced. In distributions are not, right? So this is one of the distribution grid model here. Okay, I think in distribution management system also distribution power flow. In transmission system we have we'll talk about that in detail later. But in distribution system also we have a distribution power flow, load balancing, outage management. This one we have. Okay, so if there is an outage, how you can manage it, right? So outage management system. We will talk a lot about this one, fault isolation and service restorations, okay? And then volt power optimization coming up. That is also, we will be talking about demand response, okay? We will not be talking about anything about this GIS. This is, we get it from this GIS, okay? Geographical Information System. If I am right, Azure is the one that has the software and capability to do that. I think we'll also talk about OpenDSS. Apris OpenDSS has the capability to now. Previously, we did not. But once you have this model, you can kind of combine this model into OpenDSS and run what if scenarios right on the grid. Okay. Somewhere on slide 19, someone is saying, is power quality not a priority? Power quality is definitely a priority, right? Srikant, power quality is definitely a priority. But again, you need to have that kind of capability to achieve it, right? Means technically we want, if in a simplest term, we want to have ideally unity power factor all the time, but we can't, right? We have the motors, we have transmission line impedances, and they are going to consume the reactive power, and we are not going to get unity power factor, okay? And then if you go into a little bit more detail in the power quality aspect is your harmonics, right? So anytime you turn on the computer, anytime you turn on your microwaves, or anytime you turn on any device that has electronics, you will have a harmonics, right? So it is whether are we capable, are we building a system that can handle that kind of harmonics, right? And it's very well known when you have a cricket match, when you have a here football match or basketball match, right? Every time that we have a problem of quality, power quality, because every single unit almost is turned on TV, okay? And then you have harmonics problem there. So yes, we should have a power quality as far as power quality as far as we can manage it, right? We can build the system to manage it. Otherwise, we will have to live with that one. And there are, in IEEE, there are standards, 519 standard. If you review it, you will know that there are standards to manage it. 3%, 5%, and harmonics are okay on that one. But IEEE 519 standard discusses the issues of power quality. Okay, distribution power flow, I'm just touching it, but we'll talk a lot about it in these 5 days, okay? But this is again one of the into front, okay, so you can see better. This is a control screen for the distribution power flow, and you can see now so many things, right? You want to control the transformer, you want to control the regulator, you want to control the capacitors, right? You want to do load balancings, okay? And then here, how your model looks like here is saying your model has 3 substations, that is 21 feeders, 6 transformers, so many switches, so many nodes, okay? And voltage violations, okay? You want to report, right? If you see voltage violations, okay, you want to report it, okay? And then you can just run the topology processing, a big deal, right? So if you in distribution system, if you have proper data, then you can just see how your grid look like, right? That's called it without running the power flow, just how it is connected from one node to another node, okay? And 3-phase connected. So that is again a good tool to see the topology. Then distribution power flow, okay? And these are some of the other parameters you can run, generate the reports, okay? What was the power flow, what are the losses, and what are the parameters for the power flow, what should be tolerance, right? Voltage level, and what should be the maximum iterations, what should be the KVAR tolerance, so many other things you can do on this one. But power flow is just, what is power flow, right? Power flow is simple. In this one, generally, Y V is equal to I, right? Power flow is finding the voltages and angles, okay? So here, let's say, distribution power flow uses admittance matrix. So you create a Y matrix for such a large system, okay? So distribution power flow uses admission matrix method to find the voltages, flows, and limit violation of each device in a distribution network for three-phase balanced or unbalanced systems, right? The solution technique is based on Gauss method, commonly called as the Z-bus power flow technique, okay? There are also widely, like open DSS that we are planning to talk about in APRI open DSS, they generally use backward forward the method to solve the power flow. And that was developed by Professor Custing from New Mexico. Now I think he's retired, and but he has a book on that one. And then nodal matrix, YV is equal to I. The biggest problem in software when we want to do this kind of calculation is inverting the matrix. Okay, if we take it for granted, if you have used your MATLAB, you can just say inverse this. Okay, but it's not that simple. Okay, it's not that simple when you are doing for real system. Okay, so generally there are packages that you can just use it. That is the right way to do it. But if any way, if you can program without inverting the matrix, you can solve your parameter. That is the way to go. Okay, so YV is equal to I, and if we are think about here, we want to do V is equal to Y inverse I. And if you have a 10 million node New York system or Bombay system or any large system, okay, you just can't invert it. Means it's going to take a lot of time, and probably some matrix may not be invertible because it's not fully connected. Maybe you have a lot of zeros there. So it's very important. Means inversing a matrix is very, very important, and we have to put a lot of attention to this one. But it's very simple, right? This is every single power engineer can do this one, right? YV is equal to Y. Nothing big deal here. V is equal to Y inverse I, understanding, right? The system current injection vector computed at each iteration, right? So whenever you have a load, generally we model as PQ, right? There are different loads, we'll talk about it. That generally P and Q are given, okay, at nominal voltage, what is the current, okay? And then you iterate it and come up with the solution. So you know your basically this I vector by knowing the load injection, okay? Knowing the network, you know your Y matrix, then you can calculate the voltage, again, iteratively, right? By substitutions of the factor Y matrix, the load bus voltage can be obtained as this one. Okay, so factorizing here, this one. Again, I am putting this one, but the reality is that we generally don't invert. We don't invert the Y matrix, okay? The whole matrix, okay? But probably you can just do one equation and invert it, okay? Very intelligent. Implemented that one in many softwares very intelligently. Computes current and node voltages until the absolute value difference between the scheduled load and computed injected power due to loads is within the usual tolerance. Okay, generally that is the case. In most of the time, what we learned is the voltage, right? When your desired voltage is achieved, difference between successive iteration, the difference between the desired voltage and the successive iteration voltages are very, very small. Generally millivolt difference or microvolt difference, then you solve, right? And then you say that my power flow is converged. Okay, real-time load balancing. Configuration of the distribution network is modified by changing the open or closed status of the switches on the distribution feeders. Okay, again, if your distribution systems are capable to this doing load balancing, okay, you have confidence that you have enough measurements, and whatever you are seeing on the on your software is really happening in the distribution side. Generally speaking, with with smart meters, probably we should be able to at least estimate it, a good estimate. But if you don't have the smart meter, generally you won't know what is happening exactly on every lines of the feeders. Okay, but you probably know at the feeder substation, because you can very well go and see it, right? If you are a substation manager, what is happening in each phase. That if you don't have a complete control and complete view, then load balancing is not useful thing, because it's not going to achieve it anything. But if you have reasonable confidence on the data that you are getting on the distribution side, then probably you can do load balancing. What is load balancing? Basically means we want to have the same power in each phase. That's the load balancing basically, right? We want that A phase, B phase, and C phase should have exactly the same power, right? That's the ideal case. Okay, but in distribution generally, and there are again also standards that how much load balancing are means how much unbalanced are okay with your systems. Okay. And load balancing has different objective: minimization of load, reduce risk due to overloads, optimal utilization of feeders, minimization of service interruptions, balance service of important customers for enhanced service reliability, minimization of worst voltage drop, so many things, right? But again, all these things are not done, not executed by the agents. Okay, so it's very important, means where you can, whatever you are doing your master's PhD project, where you can contribute most. Okay, that should be the thought process on that one. Manual mode of operation in the real time means you provide the solutions. You say that, okay, this is on, if you see in the last screenshot, that this is what we are thinking from the data that we are getting. This software is saying, okay, you do this, and probably you will get a better load balancing on this one. That's called manual. Okay, and then automatic is that you have the full confidence on the data that you are getting, and then you just let software decide what to optimize, when to optimize, and automatically close the switch and open the switch. So, but let's see, select the feeders to be balanced and also the amount to be transferred from one feeder to another feeder. Choose from the recommendations provided based on the amount of transferred load, possible switching, and number of violations before selecting on the final switching option. Then we have automatic that I already mentioned. The feeders to be balanced, and the amount to be transferred is decided automatically by the program. Okay. Okay, I have a question from Krishna. Is supply demand balance? Dynamic pricing for demand response is major need. Can know about it for future work in this regard. Okay, dynamic pricing for demand response. Lot of things are happening, okay, for the demand response, and we have I think we have a couple of slides. Yeah, I think we'll be spending a lot of time on demand response, on real-time pricing, and how you can leverage demand response for whatever you want to do. Means maybe minimize the losses, minimize the power, minimize the voltage, minimize the cost, a lot of things. And we'll talk about it, Krishna, at that time. Okay. Shailendra is asking, what is feeder balancing? So let's see. So if you see in this screen, you have green, red, blue, and different colors, right? So that is, red means one feeder. Okay, that is what we are calling a feeder. Okay, so one color, red, that's what we are calling feeder. So in feeder, we have three phases, ABC phases. Okay, and we want to, and if there are, let's say, just for the ampere perspective, if one phase has 200 ampere, second phase has 250 ampere, and third phase has 230 ampere, let's say. Okay, that is each phase, and we want to balance it out. Okay, so ideally we can just sum it up and divide by 3. That what is we want to do ideally. Okay, but is it possible to do that? So that's what we are saying that feeder balancing is. Okay, hope that answer your questions. Another. Okay, so very important. Multi-agent is very important again for doing, when we think about the load in major cities. Okay, I'm just New York and Bombay is coming to my mind. Okay, so But any major cities, okay, any major cities. This one is very well done, and SNC Electric has an Intelli team. If they are still have it, I don't know, but many places in the United States has been implemented. And again, we will talk about it, this multi-agent, that is the right application of multi-agent. But this one is the fault isolation and service restorations. Okay, you can once you know, again, very important point is that do you have the confidence on the data that you are getting? Okay, once you have that one, then only all these things will play into role. Okay, so fault detections detects uncommanded trip of substation breaker, right? So if you have a fault and then your breaker trips, right? So that you get this information from the SCADA points. Okay, we call it SCADA, means basically is connected to the computer, right? So anything happens to your breaker, right? Breaker has a switch, right? And if you turn it on and turn it off, right? So that breaker has a computer that will sense this and put this real-time information and to the point that we are going to read it. Okay, that's the SCADA. That's very simple explanation of the SCADA. So any device that can measure it, store it, okay, or at least communicate it to where it needs to be sent, that information. Okay, so very well you can think of as an agent. Okay, every single device is an agent that is just reading it and sending an information. Okay, but when that device is doing some kind of intelligent work, okay, then we can call it an agent basically. Okay, so detection, locations, okay, using telemetry, fault indicator information, or input from user, or input from the smart devices, okay, to figure out where is the problem, okay, where you don't see the voltages, okay, what or what happened, who sees the fault current, who did not see the fault current. So a lot of things. Then isolations. Once you know where is the fault, you can isolate it. Okay, and the isolation has to be minimum, right? What is the minimum isolation you can do so that all other customers will get the power, right? So that's the isolation is very important. Minimum isolation. Wherever there is a fault, you just isolate that portion. Sometimes is not in our control because your feeder, your line is so long that you have to shut down every single customer to remove the fault. Okay, and once you isolate the fault and if it is repaired, then you go for the restorations. Okay, so unfaulted feeder sections upstream and downstream. Okay, then you can once you isolate the fault, those customer will automatically have the power basically, right? And then service restoration. Once fault is fixed, you can just press the button, my fault is fixed, and then it remembers. Think about it as an agent. It remembers what was the configuration before the fault, and now you just bring back that configuration. What you do is just send signals to those remotely controllable devices, and they just bring back to the normal status as what they were before the fault. Okay, so that is fault isolation and service restoration. Okay, so I think we talked a lot about this, okay, and I think I'm very confident that most of you now understand what is happening with at least very big understanding of the power grid and what are the capabilities that we have and what are the things missing, okay. And I think we are almost ready to talk about agents now, I think. Okay, so if you don't mind, I think let's take a 5 minutes break, okay, and then come back. So just quickly restroom and then we'll come back. Okay, so exactly 5 minutes. Okay, no more than a second. Okay, so let's take a 5-minute break and then let's come back and start talking about it. Okay, and then probably I will ask if you have any question before we start. Now this will I will say a little bit more different than what you know, right? So you have to put a little bit more efforts to understand. Okay, and probably more like computer science of this one. Okay, so we need to learn a little bit of computer science okay, on this one. So So let's come back and let's start talking about it. Okay. So so what is agent? Okay. Thank you guys. Okay. So I will mute myself here and then I will come back in 5 minutes. Okay. Okay, again, good morning and good evening there, probably. So, okay, now who is writing on the screen? I think that's a good thing to have, but it's not the right time to write it. Dr. Rohit or Dr. Prerna? Is there a way we can?
Yes. What happened?
Is there a way we can remove that writing on the screen?
Okay, somebody is writing. Yeah. There is a challenge. Yes. Yeah, I got the point.
By mistake, probably someone wrote it. Yeah.
Yeah. Participants are kindly requested, because though the link has only been shared with those who are registered participants, we will request not to scribble on that screen, please.
Yes. There is a setting in our Zoom.
Yeah.
I think you can stop it. Means we can stop it. Yeah. So, but I think it would be very annoying.
Yes. I got the point. Somebody has scribbled down.
Yeah, if someone can erase it, that probably Dr. Prerna, you think you can erase it? I don't know. I am not able to do it on my screen.
No, I think some host Ashish, if you can hear, if you can erase it.
Yes, sir. I'm trying, sir.
Yeah.
Okay. So let's start talking about it. Okay. So what is an agent? Very simple, very basic. Okay. Remember again, this is a computer science, and you have to pay attention to it to understand it. Okay. There is not a single definition of an agent that is universally accepted, right? An agent is a computer system that is situated in some environment. Okay. That is this environment. Okay. And then this is a system. Okay. So agent is a computer system that is situated in some environment and that is capable of autonomous actions in this environment in order to meet its design objective. Right? Means we talk a lot about it, right? I mean, at least from the perspective of the power grid, right? So power grid is our environment basically, right? And then computer system like EMS, you can think about this. You can add this one, okay? But EMS is not distributed, right? Decentralized. EMS is kind of centralized, okay? So a little bit more into it, okay? But very simple, agent is a computer system that is situated in some environment and that is capable of autonomous action in this environment in order to meet its objective. Like think about one of the restorations, right? If we do it everything from start to finish that we just discussed right here, without not a centralized and without intervening, that is the ideal case of the agents or multi-agent system. Okay. Two key problems. Okay. So agent design and society design, right? How do we build agents capable of independent, autonomous action so that they can successfully carry out tasks we delegate to them? Very simple, right? That is first question. How do we build agents that are capable of interacting? Okay, interacting meaning cooperating, coordinating, and negotiating. Very three big words, right? Cooperation is a big thing when you have a different objectives. Okay, so how do we build agents that are capable of interacting with other agents in order to successfully carry out those delegated tasks, especially when the other agents cannot be assumed to share the same interest or goals? Okay, give me 1 second. Okay. Very two key problems. Okay, cannot be assumed to share the same interest and goals, right? Very important. So that is the problem that we have with the agents. Now, a multi-agent system. A multi-agent system is one that consists of a number of agents, okay, which interact with another. Okay. In the most general case, agents will be acting on behalf of users with different goals and motives. I think of as a generating company, transmission company, right? Distribution company. All these are three agents, right? So in the most general case, agents will be acting on behalf of users, right? With different goals and motivations, right? So everyone has a different goals, right? But on these three companies, the one goal is for sure that everyone has to make most profit. Okay, everyone has to make more profit. And now how they do it, okay, that is the part that is important. To successfully interact, they will require the ability to cooperate, coordinate, and negotiate with each other. Much people do, just like what we do, right? When we have a problem, we sit together in a company, right? And then figure out what is the problem, why is the problem, is there a way we can solve it? It is coming from our system. If it is not coming from our system, whose system is coming from? So it's very important. It's very similar. Okay, is there a way we can build such kind of systems, multi-agent system, that is kind of doing human intelligence basically? These questions should be answered for developing multi-agent systems. How can cooperation emerge in societies of self-interested agents? Right? Exactly same thing as Genco, means generation company, transmission company, and distribution company, self-interested, right? What kind of languages can agents use to communicate? Okay, very important, right? If we speak different languages, then a very big deal, right? To just understand the language is a big problem, okay? How can self-interested agents recognize conflict and how they reach agreement? Okay, if they are self-interested, okay, can you hear me? Someone just write yes.
Yes, sir, we can hear you, sir.
Okay. Yes, reward-based systems with protocols. Okay, Srikant, I think very well said. So how can self-interested agents recognize conflict and how can they reach agreement? Okay, nevertheless, the word is, okay. How can autonomous agents coordinate their activities so as to cooperatively achieve goals? Okay, restoration, one problem is restoration. We are going to talk about a lot of problems, okay, that multi-agent system can solve in Power Grid, okay. But how can autonomous agents coordinate their activities so as to cooperatively achieve goals? Okay, may not be optimum, but achieving the goal, okay, in a timely manner, I would say. While these questions are all addressed in part by other disciplines, okay, notably economics and social sciences, what makes the multi-agent systems field unique is that it emphasizes that the agent in question are computational, information processing entities. So what are the agents? Okay, so what are the agents? Should have computational and information processing. Okay, agents should have computational power basically and information and processing entity, means information processing module they should have. If you are not muted, please mute yourself. What are multi-agent systems? Okay, so think of this as a power grid, right? Whole power grid. The environment is a power grid, okay? And think of these three entities, okay? Again, same thing is coming to my mind. Generation company, transmission company, distribution company, or multiple generation company, multiple transmission company, multiple distribution companies, okay? And their actions are definitely is going to impact the power grid operation. If it is generation, transmission, or distribution, right? So now if you see here, so this is organization. So this is the dotted line is one organization, one company, basically. Okay, one company. So in company inside also you have agents, think about, right? And they are interacting. And then when they are making decisions on the aspects of the power grid, is going to influence the power grid in that particular aspect. Okay, 1 second. Please mute yourself, okay, if you are not speaking related to our course, and I will appreciate. Thank you. Okay, so original, and then we have interactions that is shown by this arrow, right? So that circle is kind of agent, think about this, and then they are interacting, and then they are acting on this power grid. Now, if you see here, there you have multiple or kind of conflicting actions on the environment from the agents, right? So that is one thing that happen. Now you can have multiple organizations affecting the power grid in multiple different ways, okay, conflicting actions. So we have to design a multi-agent system that is not create a conflict, okay? That is very, very hard to do that, okay? But if you have your own system, probably, yes, you can probably come up with a system that can come up with a multi-agent system that can achieve the desired objective, basically. So thus, multi-agent system contains number of agents, right? So these are all circles are kind of agents, right? And then these agents interact through communications. So you have a communications between these agents, okay? These are the communication. Different spheres of influence, okay, which may coincide, right? Different spheres of, so here on the environment, the circle that you are seeing, that is the spheres of the influence, right? They are these spheres of influence, okay? And will be linked by other relationships, other organizations, okay, other organizations. It's not shown here, but will be linked by other organizations. If we have a communication between this circle, dotted circle with another dotted circle, then we can say that multi-agent system, multiple multi-agent systems are interacting. We can say that. We need a model of the environment in which these agents will act. For us, power grid, right? And very well established model means, right, in most part. But it's evolving every time we have new device coming into the power grid. The model has to be evolved. Agents simultaneously choose an action to perform, and as a result of the actions, they select an outcome. In mathematical form, if you see this one, agent I action and agent J action will give you some kind of output, right? Some kind of output. The actual outcome depends on the combinations of actions. Assume each agent has just two possible actions that it can perform, C and D, cooperate or deny, if just for the understanding. Okay. Agent, we call it multi-agent encounters. Okay, multi-agent encounters. Multi-agent system is interdisciplinary. The field of multi-agent system is influenced and inspired by many other fields. Okay, many other fields. Economics, philosophy, game theory, okay, logic, ecology, social sciences, everywhere multi-agent system has been applied. Okay. Agents as a paradigm for software engineering. Software engineers have derived a progressively better understanding of the characteristics of complexity in software. If you have worked on any software, if you have worked, you can know that there are tons and tons of APIs and tons of methods, functions, okay, that you have to interact. And in earlier cases, where at the time when the softwares were evolving, So anytime they create a new release, new version, you will see that they break the old version. Okay. Now I am seeing that is happening less and less, but you are still seeing some things will work in version 1, like MATLAB. If you take 2019 version and 2022 version, and if you have done something unusual in MATLAB in 2019, it won't work in 2022. Okay, but generally in Microsoft, they are their motto is that it should work for every previous version. Okay, and that is one reason Microsoft is so famous, right? So if you have something in Microsoft, even after 10 years, you should be able to open it. But in MATLAB, if you have something, okay, then probably chances are you won't be able to open it after 10 years. So much changes are happening in that one. Okay, so complexity is very big issue. Okay, it is now widely recognized that interactions is probably the most important single characteristics of complex software. Interactions, how you are interacting. Over the last 2 decades, a major computer science research topic has been the development of tools and techniques to model, understand, and implement systems. Yeah, I don't know why my mic is going muted every time. Okay, Shailendra, can you hear me now?
So we can hear you.
Okay. Okay. So anytime if you don't hear me, just say something or write me because I'm closely observing the chat messages. Okay.
Yes, of course, sir.
Over the last 2 decades, a major computer science research topic has been the development of tools and techniques to model, understand, and implement systems in which interaction is the norm. Okay. So, like I said, a lot of things are evolved, and we have set tools and set methods now. So generally, you will see less failures from one version to another version. Agents as a tool for understanding human societies, big deal, right? Multi-agent systems provide a novel new tool for simulating societies, which may help shed some light on various kinds of social processes. Okay, very big advantage of President Obama's campaign. They leverage all social media power to this one. Okay, so from that data, social media data, they can figure out that which area is supporting or opposing the views that they are presenting. Very big deal, right? And then once you know that information, then you can go campaign there and try to change their views, right? What they are understanding when you are speaking, right? So very big deal. Agents as a tool for understanding human society. So we can make some kind of this kind of applications. Okay, for educations is very important. So when I say education, means understanding where do you see that which area, means if you are a prime minister or what you call chief minister of a state. Okay, if you want to figure out if I have set amount of money where I should invest so that the most uneducated students will get the education, right? That is a big question to figure out that one. And if we have that kind of a system, we build it, then we can invest our funds at the right location, right time, and we can get right results, right? Possibly. We can put that same perspective in the power grid as well. Okay, so multi-agent systems is primarily a search for appropriate theoretical foundation. Okay, somehow my E is smaller. We want to build systems of interacting autonomous agents, but we don't yet know what these systems should look like. Right? You can take a neat or scruffy approach to the problem, seeing it as a problem of theory or problem of engineering. Okay. A problem of engineering means putting all together, and generally we call it that we know the outcome. Now we are searching that what all things that we need to put together so that we can achieve that outcome. It's kind of engineering output. Problem of theory is that you theorize something, okay, and then come up with some kind of methods to achieve it, right? So problem of theory and problem of engineering. This too has analogies with artificial intelligence research, okay, and lot is happening, okay. Every 10 years and 15 years, lot happens in AI, but this time is really happening. A lot of things are changing in AI, and AI is changing a lot of things in our lives. Isn't it all just distributed or concurrent system, multi-agent system, they were asking. There is much to learn from this community. Okay, distributed and concurrent system. When we say community means when you attend a conference, okay, and then everyone is doing research and they are presenting. So we call it a power community. Okay, if you are Power Globe member, if you are not, then you should Power Globe member. Then we call it the Power Globe community. Okay, so that means distributed. So when they have this kind of conferences, they have this kind of group discussions where they see that there is a problem and there are no methods there, and everyone working to find the solution for that kind of problems. Okay, so that's the meaning of the community here, distributed or concurrent systems community. Agents are assumed to be autonomous, capable of making independent decisions. So they need mechanisms to synchronize and coordinate their activities at runtime. Very important, right? Coordination, cooperation and coordination. So agents are assumed to be autonomous, capable of making independent decisions. So they need mechanisms to synchronize and coordinate their activities at runtime. Okay? Otherwise, they won't be able to perform because they need some information and they need to act on an environment, right? On the power grid. If they are acting it, if there is action is not going to change anything, then there is nothing agent can do, right? So agent has to have input and output, or some kind of sensors and actuators, right? Access to it. Agents are self-interested, so their interactions are economic encounters, right? So we want that agents, when we build it, we want that it should perform the desired job, right? Isn't it all just economics or game theory? Okay. These fields also have a lot to teach us in multi-agent system. Okay. As game theory provide descriptive concept or concepts, it doesn't always tell us how to compute solutions. Okay. We are concerned with computational resource-bounded agents. Okay, computational and resource-bounded. Very important, right? Means we don't have infinite resources. We have very limited resources. And when we talk about real system, then very, very, very limited resources. And we want to utilize those resources to the best, to get the best possible outcome utilizing those resources. So very important. Some assumptions in economics or game theory, such as rational agent, right, may not be valid or useful in building artificial agents. Some assumptions in economics or game theory may not be valid or useful in building artificial agents. Okay, not useful. But the reality is everyone has a different rationality, right? Means how you grew up, that thought process governs your decisions, right? What you have learned, what you have experienced, right? So similarly in the system also, that those experiences we need to build when we are building a multi-agent system. Are agents just objects by another name? Objects, what is object? When you compile any C code or Java code, you get .class or .obj, okay, file. That is what it means we are here, is objects. So objects encapsulate some state, communicates via message passing, right? has methods corresponding to operations that may be performed on these states. Okay, what are objects? Encapsulates some states. Okay, some information basically. Because when you run a method, you need some kind of input, some kind of equation, some kind of algorithm, or some kind of logic, right? To act on that information and then come up with the output. As methods corresponding to operations that may be performed on this state. Okay. Objects sending message is effectively responsible for ensuring that the address is accurate, right? We don't want to send a wrong message, right? We don't want to send a message. If we are doing restoration, we don't want to send a message to economic agent when we are doing restorations, right? Or similarly, if you are dealing with power engineer, we don't want to be sending a message to, let's say, some aerospace engineers, right? Or aerospace agents in somewhere, not related, right? So object sending message is effectively responsible for ensuring that the address is accurate, the method corresponding to the message exists, and that the parameters are adequate. These things, right? Address is accurate, message exists, and parameters are adequate. Okay, those are the things are very, very important that we need to be careful when we are designing agents. Agents and objects. Main differences. What are the differences between agents? So this one are objects we talked about. All these in objects. Okay, that is dot class file if you have worked on Java, or dot obj file, or dot out file if you have worked on Linux. Right? Here, when we are talking about agents, agents are autonomous. Agents embody stronger notion of autonomy than objects. And in particular, they decide for themselves whether or not to perform an action on request from another agent, right? So if, because when we are talking about multi-agent system, they have to collaborate to achieve something, right? Let's say restoration. Okay, so they want to restore the system. So and each does not have full system knowledge, right? So then they have to communicate, right? And then communicate and act. Okay. So when to act? Agents, unless and until the agent is not acting with the information that the agent received, okay, then that agents are not autonomous. Agents are smart, okay, capable of flexible behavior. Please pardon the behavior spelling because this different English, UK and US English, okay. And the standard object model has nothing to say about such types of behavior, okay. So capable agents are smart when capable of flexible behavior, and the standard object models has nothing to say about such types of behavior, okay. Doesn't. So that's the difference between objects and the agent's behavior. So agent doesn't have objects. Agent generally have a behavior, we call it, okay. Agents are active. A multi-agent system is inherently multi-threaded, okay, because Java, we are using Java, and Java is multi-threaded programming. And that is why we are getting that multi-threaded and capabilities in the agents, okay. So a multi-agent system is inherently multi-threaded in that each agent is assumed to have at least one thread of active control. Each agent is active. Each agent is active basically, okay. Objects do it for free, okay, means .java, and that's it. Multi-threaded is running multiple programs at the same time, Shailendra. Multi-threaded means multiple programs you are running at the same time, or kind of asynchronous, okay, asynchronous way on this one. Agents do it because they want to. Agents do it for money or profit, okay. So that is the difference between objects and agents. Aren't agents just the AI project? Right, when we talk about this one, okay. Isn't building an agent what AI is all about? Okay. AI aims to build system that can understand natural language. Very important, right? Recognize and understand scenes Still not there. We have not been there yet. Use common sense. Think creativity. It is all of which are very hard. Okay, that is AI is trying to do that. Okay, just by seeing the picture, you can say that this is airport. Okay, how you can say that? You can probably see couple of family members, couple of people carrying the bags, trolleys, so many things, right? So just understanding, just having that information, AI can say, okay, this is a scene of a airport. This is the scene of a hospital, right? If you see that you have an oxygen bottle, doctor wearing the white coat, right? Stethoscope, and there are people walking because they are injured. You may be seeing some blur, some so this is kind of a scene, understanding the scene. Okay, understanding natural language means when we speak, either you speak and me speak. Okay, or so understanding, probably if you have heard about Alexa, right? Very well built, right? We can call it an AI marvel for that one. Okay, so in most United States, every house, most house will have an Alexa. It's just a speaker, and it has an internet connections. And then if you can Google it, okay, and you can, if you ask any general question, you say what is the temperature in Jaipur, Rajasthan, and immediately it will say that this is the temperature and this is the maximum and minimum temperature throughout the day. Or if there is rain is going to happen, it will tell there is rain is going to happen. Okay, if I say who is the prime minister of so I'm talking with the device, natural language processing. Okay, so Alexa, the built by this Amazon company. Okay, so when I'm talking, who is the prime minister of India, and then he will say Narendra Modi, prime minister, or anything, any general knowledge question. Okay, and it has even crawled the web. So if something available on the web, somehow it finds that information and bring it to you. So I just ask, and it will. So my kids, they play math game with them. Okay, so they ask simple addition, subtraction question. Even Alexa asks very detailed questions, 2-level, 3-level deep questions. So you have to do 2-3 level of calculation to achieve it. So that's a natural language processing, understanding. So conversing between human and the device. Okay. So don't we need to solve all AI to build an agent? Okay. When building an agent, we simply want a system that can choose the right action to perform. Typically a limited domain, right? Means an agent cannot restore the whole system. One agent cannot. Okay. We do not have to solve all the problems of AI to build a useful agent, right? Our motto is very simple, this one. Little intelligence goes a long way. Little intelligence. If you heard about edge computing, okay, so edge computing is kind of a single agents. Okay, so you can think of multiple edge computing working together to achieve something that you want to do. Okay, so then we can call it that as a multi-agent system. Any questions? Okay, Srikant is asking, what is the objective in seeing power system as a multi-agent system? The powers, we are distinguishing, remember our first slide, let's say slide 41. So think of this environment as a power system. Okay, and when we are saying system is an agent. So we are not seeing power system as an agent, but we are seeing multi-agent system to achieve better operation of a power system. Okay, that's what we are seeing here. Okay, that's we want to do it. Okay, and we'll probably you will get more detailed answer when we talk about the applications of multi-agent system in power system. So just hold on that one. Okay, Srikant. So little intelligence, we have just a little intelligence. Okay. Environments accessible versus inaccessible, very important. An accessible environment is one in which the agent can obtain complete, accurate, up-to-date information about the environment state, right? So when we talk about the generation company, transmission company, and distribution company, so transmission company has no knowledge about generation company. Okay, so that is inaccessible. Generation company inside knowledge is inaccessible. Similarly, generation company has no knowledge about the transmission companies. Okay, but there are ways people can figure it out. Okay, once you have enough information, then you can figure it out. But accessible is the information that you can accessible. Okay, so an accessible environment is one in which the agent can obtain complete, accurate, up-to-date information about the environment state. Okay, so for the transmission company, if it is monitoring, let's say 10 transmission line, okay, major transmission line that spans from north to west and north to south and east to west, okay, then that company has the complete knowledge about that transmission lines. Okay, most moderately complex environments, okay, including, for example, the everyday physical world and the complete internet, okay, are inaccessible. Okay, you can access internet limited, right? You can't access everything at one time. The more accessible an environment is, the simpler it is to build agents to operate it. Very simple, right? If you know the information, then you can act on it. If you know the environment, if you have the information about the environment, then you can access it. Okay, so someone, Swati is requesting, can you show slide 21? Okay, so slide 42 right now we are. Slide 21 is this one, real-time load balancing. Okay. Okay, I don't know, Swati, what you mean, but you will get these slides. Okay. I think Dr. Prerna will share these slides with you all. Okay, once we are done with the course. Okay. Hope that helps, Swati. Okay, so environments, accessible versus inaccessible, very clear. Okay. Environment deterministics versus non-deterministics. Okay, deterministic is very simple, right? What is deterministic? If I say 1 + 1, right, that is in very simplest way. That is only one answer to. Okay, non-deterministics is what will be the load, okay, in next instant of time. That is non-deterministic. Okay, what will be the output from the solar and wind? Non-deterministic. There is no way 100% accurately we can predict the solar output and wind output. Okay, non-deterministic. And when you have this non-deterministic devices or actions on your systems, okay, then your environment is kind of so for us, power grid and environment is non-deterministic. But yes, some part of it is, right? Some part of it is because generator output, right? We can control the generator output. Okay, and again, it depends on the load as well. But we can basically, at least base load generation, like nuclear power plant, coal power plant, those are we consider base load generators. So we know that are deterministic. We know that this is what we are going to come out every single moment in time. 1000 megawatt, 500 megawatt, no matter what it is, these 5 generators are going to give us. Okay, very deterministic. Optimization problem. Okay, so if you come up with any optimization problem, okay, if you put a little bit boundary to it, means proper constraint to it, right, upper bound and lower bound constraint, then probably your problem may be deterministic, right? Then you can solve it, right? But as soon as you remove those constraints, right, then probably your is non-deterministic, your optimization problem. And if you have selected some variables in your optimization, okay, so then those variables are fixed. Okay, so that for that fixed problem, you can say that my optimization is deterministic. But because you fix those parameters, right, and when you change those parameters, then it's non-deterministic, right? So generally, I would say any larger level problems in the power grids are non-deterministic problem. Okay, that is not one single solution. There are multiple solutions exist. Okay, but here what we say, a deterministic environment is one in which any action has a single guaranteed effect. Has a single guarantee, any action. Okay, single guaranteed effect. Okay, so if I say that generator set point, if I change, if let's say generator is running as 2 megawatt and I want 2.2 megawatt, if I change it, so if I did the action and it is going to give me the 2.2 megawatt. Okay, so deterministic environment is one in which any action has a single guaranteed effect. There is no uncertainty about the state that will result from performing an action. Okay, there is no uncertainty. Okay. This one. The physical world can, to all intents and purposes, be regarded as non-deterministic. For us, our world is power grid, right? It's non-deterministic. We don't know what will happen next instant in time. Okay, in a power grid, power system perspective, we are talking about. Okay, non-deterministic environments present greater problems for the agent designer. Non-deterministic environments for power grid, right? Means if you want to build something there, it's gonna be challenging. Okay, it's gonna be challenging. For us, it's gonna be challenging. Okay. Episodic versus non-episodic. That is definitely you can relate with your series, right? Any series that you watch in TV. Okay, now it's now more on demand. Okay, but if it was not on demand, that is kind of episodic, non-episodic. Let's see what we have here in the perspective of agent. In an episodic environment, the performance of an agent is dependent on a number of discrete episodes. Okay, with no link between the performance of an agent in different scenarios. Okay, that is one thing. Again, in an episodic environment, okay, I know I'm going to bore you on this one. Remember, this is not, I'm trying hard to link this with power system as I can. Okay, there is no such book available that links all this information with power system. Okay, so anything that we are saying here, we are understanding that kind of almost new knowledge here. Okay, so in episodic environment, the performance of an agent is dependent on a number of discrete episodes, with no link between the performance of an agent in different scenarios. There is no link between them. Okay, that's called episodic environment. Okay, episode 1, episode 2. Generally, we have link between episode 1 and episode 2 in the TV series, right? Or not, right? Maybe characters are the same, and if you are watching CBI, right, you can relate that, right? So you have different incidents, but the characters are the same, and then different episodes. For us, episode, you can think of a fault, right? Fault on the transmission line, fault on the generator line. So different scenarios, different places. Okay, episodic environments are simpler from the agent developer's perspective. Okay, because the agent can decide what action to perform based only on the current episode. Okay. Episodic environments are simpler from the agent developer's perspective because the agent can decide what action to perform based only on the current episode. It need not reason about the interactions between this and the future episode. Okay, no. Okay. Environment. Static versus dynamic. Okay. So we talked about little intelligence, then accessible versus inaccessible. Okay. And deterministic versus non-deterministics. And lot, you can actually philosophical economics, people can spend like almost 1 hour on just the concept of episodic and non-episodic. Okay. Static versus dynamic. For us, definitely static versus dynamic, right? So when we run a power flow, right, that is static power flow. But when we run the power flow timely, means every few seconds, then we call it dynamic power flow, right? Time series power flow. Okay, time series analysis. Okay, static analysis, dynamic analysis. Any DC circuit solution is a static analysis. Any DC circuit solution. Okay. Any time domain solution is dynamic analysis. Okay. A static environment is one that can be assumed to remain unchanged except by the performance of actions by the agent. Okay. A dynamic environment is one that has other processes operating on it, and which hence changes in ways beyond the agent's control. Okay, so that's the dynamic environment, right? So the power system is a dynamic system. Power system operation is a dynamic system operation. Okay, continuously changing, continuously changing, right? And continuously different loads coming in, different generator coming in. So power system operation is dynamic operation. Okay, other processes can interfere with the agent's actions. Okay, definitely, right? Because that's the when agent takes actions, and so agent sends a control message, a control signal to a breaker. Okay, and if breaker doesn't operate it, okay, for some reason, maybe some physical constraint, some malfunctions. Okay, so now it is interfering, right? The physical processes is interfering with the actions of the agent, right? The physical world is highly dynamic environment. For us, physical world means power grid, right? Power grid is a highly dynamic environment. Power grid has highly dynamic environment. Okay. Now, discrete versus continuous, right? Accessible, inaccessible, dynamics, static, episodic, non-episodic, right? So these are the environment for the agents we are talking about. Okay. Discrete versus continuous, any simulation that you do is discrete simulation. Even they call it time domain simulation, but it's still discrete because we are doing for some kind of a time step we are taking every microsecond, every nanosecond. If someone mentions RTDS, I think if I'm right, we can go up to nanoseconds, and some maybe picoseconds you can do simulations. Okay, and depends on what kind of simulations we are interested, right? What we want to understand. We want to understand transient behavior, dynamic behavior. We want to understand the switching behavior, right? So it depends, but everything generally, anything related when you are doing this discrete. Okay, discrete. An environment is discrete if there are fixed finite number of actions and percepts in it. Okay. Russell and Norvig give a chess game as an example of a discrete environment because this is computer science. Okay. Taxi driving as an example of a continuous one. Okay. Yes, taxi driving is a continuous one. Continuous environments have a certain level of mismatch with computer system. Absolutely, right? So we say that RTDS is real-time digital simulator, but it's not, right? Because it's going to run at picosecond, nanosecond. Okay. So it's not, I mean, though we call it is real-time simulator, because that is the best we can do what we have right now, and then we are relating that to the real-time system. So continuous environments have a certain level of mismatch with computer system, that obvious reason. Okay. Discrete environments could in principle be handled by a kind of lookup table. Okay, discrete environment. Agent architectures. Kolbling considers an agent architecture to be specific collection of software or hardware modules, okay, typically designed by boxes with arrows indicating the data and control flow among the modules. Okay. We will show in one of the example all the flows between agents. A more abstract view of an architecture is as a general methodology for designing particular modular decomposition for particular task. Okay, a little bit detail on this one. Okay, but we'll see the interactions between agents when we talk about the applications. Okay, hybrid architecture. Many researchers have argued that neither a completely deliberative nor completely reactive approach is suitable for building agents. Deliberately and reactive. Okay, we don't need together, right? we need together, not completely deliberative or not completely reactive approach. Reactive means react on the action. Something changes, you react it. Okay. Deliberately, you are doing for deliberation, right? Deliberately, you are doing it. Okay. You are deliberately turning off, if you are a taker, right, on the power grid. So you are turning off deliberately one of the important breaker, right? So that's a deliberation. We don't want that, right? They have suggested using hybrid systems which attempt to marry classical and alternative approaches. Okay. An obvious approach is to build an agent out of two, okay, deliberative and reactive, okay, subsystem. A deliberative one containing a symbolic world model which develops plans and makes decisions in the way proposed by the subsymbolic AI. Okay. What is subsymbolic AI? Subsymbolic AI is the set of alternative approaches which do not use explicit high-level symbols, such as mathematical optimizations, statistical classifiers, and neural networks. Okay. A reactive one, which is capable of reacting of events without complex reasoning. Okay. When you have complex reasoning, you can definitely model complex reasoning in our power grid perspective. Okay. But it takes time, right? It takes a deeper understanding. And generally, when you have a multi-agent system, itself is complex when you talk about multi-agent, because a lot of interactions between agent, and you have to be very attentive, okay, when you are designing your multi-agent system. Okay. But once you design it, it saves a lot of the time, human time. Often the reactive component is given some kind of precedence over the deliberative one. Okay. Often, generally, when we are designing multi-agent system, we want agents to be reactive rather than deliberative. But depends on the application as well, what deliberation you want to achieve from your agents, right? So it depends on the application. In such an architecture, an agent's control subsystems are arranged into a hierarchy, okay, with higher layers dealing with information at increasing levels of abstraction. When generally it's very true in our human society as well. When you go higher and higher, it means when you become a CEO, and if you are a coder, right, means power engineer, coder basically, right? Then if these two people are talking, right, so CEO is going to talk about very abstract things, then you think about it, very abstract, very high level. And then when as a power engineer, you will be talking about very detailed, right, very detailed, what needs to be done, what is step one, what is step two, how we can achieve it, right, what we can program it. So very important means, right, that knowledge, details are very important. Building agents, you need to know what you are building it, why you are building it, right? Hybrid architectures, a key problem in such architectures is what kind of control framework to embed the agent subsystem in to manage the interactions between the various layers. Again, a key problem in such architectures, means hybrid architecture, is what kind of control framework to embed in the agent subsystem. Okay, agent subsystem is generally, we call it a behaviors, okay, or methods in terms of the computer science language, okay, to manage the interactions between the various layers, okay, between various layers in the architecture we are talking about. So horizontal layering and vertical layering, okay. So this is kind of horizontal layering and vertical layering that we are talking about. This is vertical layering on the right side. So horizontal layering, layers are each directly connected to the sensory input and action output. Sensory input and action output. Okay, that is horizontal, okay, architecture. In effect, each layer itself acts like an agent, producing suggestions as to what action to perform. Okay, so each layer is an agent, okay, receiving some input and coming up with some output, okay, or some actions. Okay. And then we have vertical layering. Okay. Sensory input and action output are each dealt with by at most one layer each. Okay, vertical output we are talking about, right? One layer each. Okay. So then you have a flow that you can go from one agent to basically an agent and then come up with an action. Okay, or every agent, or you can have a flow with multiple agents, right? You are sending, receiving the information, and you are deciding on that one. Okay, so different kinds of architecture. Okay, you can have a flow from one layer, second layer, and then second layer is acting. Okay, you can flow and then you can have an n layer. How you want to configure your architecture for depends again on the applications. See, what is the disadvantage that we have here is not a fault tolerant, right? This is, so even one agent is gone, then we are in trouble. Means we are not going to get the job done. Here, even one agent is gone, we still have partial system running, right? Introduces bottleneck in system, in central control system, if we have a central control system, right? Okay, so I think we talk a lot about different things. Now let's talk about some different types of agents. Okay, so I think let's take 5 minutes break again. Okay, and come back, restroom break I would call it, and then let's talk more about it. Okay, and then we will, I think, start talk. We still have some more, and then we will start talking about the applications here. Okay. So we have a couple of more slides before we go into the applications of the agents. Okay, so let's take 5 minutes break. Okay, on this one. Thank you. 1 more minute, okay? We'll start in 1 minute. Okay, Shailendra, I think I received your text message and I think, yes, you are right. I think I will do 15 minutes break, okay? Maybe next break we'll do 15 minutes, okay? And from next time, every 2 hours we'll do 15 minutes break, okay? That will a little bit help everybody. So every 2 hours we'll do, means one big break, and then every 1 hour we'll do like 5 minutes break, okay? So I think that would help. Okay, then I think we are already ready. So let's talk about software agents, mobile agents, right? Different types of agents that we have. Software agents. And technically, all agents are software agents, like because we are building software, okay? What we call it software agents, then mobile agents, okay? Reactive agents, cognitive agents, hybrid agents, interface agents, middle agents or intermediate, different means what you are trying to achieve, means how you are going to present it, okay? That's probably the difference of agents. So what are software agents? Software program that can perform specific tasks for a user and possesses a degree of intelligence that permits it to perform parts of its task autonomously and to interact with its environment in a useful manner. Very simple, right? Interact on the environment, that is all the agents are interacting with the environment, that is for sure, right? Means without that we won't be have a agent. Reactive and deliberative actions. I already gave Subal for example for the deliberate, right? Deliberate is for doing attack, right? If you are someone is attacking, cyber attack, right? Someone is turning off the breaker or disconnecting the generators, okay? So that is a deliberative. And reactive means any agents are reactive. Means if let's say if you have a fault, okay, so as soon as we'll talk about it, but as soon as you have a fault, what things can happen, right? When you have a fault, first thing that can happen is you may have a large current, or you may have a lower voltages, okay, depends on what kinds of fault you have, right? And then so when you have this kind of something happening in the power system, and then your agent reacts, either send a message or do some calculation. That's called reactive agent. But again, we'll talk about it. So just hold on that we will start talking about the applications, and we'll take 1 or 2 detailed applications on that one. Okay, so software program that can perform specific tasks for a user and possess a degree of intelligence that permits it to perform parts of a task autonomously and to interact with his environment in a useful manner, right? So performing task autonomously is very important for us. Any agent, if it's not performing autonomously, then it's not an agent, right? That's what our definitions of agents are. An intelligent agent is a computer system that is capable of flexible autonomous action in order to meet its design objective, right? That is called intelligence. So anything, little intelligence, right? Little doing something with the information, right? That's the intelligent, doing something with the information, okay? And here when we say flexible mean that the system must be responsive, proactive and social. Okay, that's the flexible meaning of the flexible. Responsive, proactive and social, but does not mean that we have to have all these three components when we are developing. You depends again on the applications, right? But these are the definitions how in the computer science, how agents are defined, right? One is software agent, and then we have a mobile agent. I think we'll show the applications of mobile agent that we have done. And so mobile agents are software agents, right? I mean, like I said, each agent is definitely a software agent, right? Because it's going to take some information, either it's going to act on the environment or do something with that information and pass it to another agent, okay? So any agent has to be a software agent, okay? But any agent may not be mobile agent, right? So mobile agents are software agents capable of moving from one machine to another automatically, okay? Mobile agents are software agents capable of moving from one machine to another machine. Extremely useful, okay? Extremely useful. And then we'll show you the example how we have used this agent, okay? Or an agent, I would say. One advantage compared to a static agent residing on a particular machine is that this can decrease the network communication load, right? Example, video selection on a specific topic. Big one, right? Means if you have 5 computers and you are trying to find one video from these 5 computers. So we don't want that all videos would come to one agent, right? Or one computer and then analyze. That is going to take forever for a normal human computer. I mean, normal PC, normal home computer, just impossible. Even we have to, if you have to download 1 terabyte or 2 terabyte of data, right? Unless you have an IIT network, okay? I mean, just talking about the house network is gonna take a lot of times, right? So it's good idea to have this kind of agent, send it to that location, do analysis, and just pick the video that really you are interested, rather than bringing this. So this is in power system perspective. We'll see what is the application. I don't want to talk about right now, okay? So but we have used mobile agents, okay, and see why we have used it and how we have used it. Then we have reactive agents, okay? Agents which only react to external stimuli and do not communicate directly or at all except for control signals, okay? So external stimuli, like I already mentioned about fault. So if you have a fault, right, and your agent is acting with that information, and then maybe send a control signal, okay, that's the reactive agent we are calling. Some agents decide what to do without reference to their history, right? They base their decision making entirely on the present with no reference at all to the past, okay? Generally, most of the agents are like that only, right? But if when you are building some kind of AI, then you will have some kind of past that you will see and use it in the calculations, okay? Or automatically your AI model will do that because you have trained your AI to do so, but not probably in there, definitely not in reactive agents, okay? Agent has to choose among several tasks that it can execute at a given time, right? So task means, we call it a behavior, means methods or functions, okay, in a computer language. And so you have many methods, and then you can execute all the methods simultaneously, one by one, depends on how you what you want your agent should do, right? So agent has to choose among several tasks that it can execute at a given time. We call such agents purely reactive. Okay, so you have actions and then you got it, means purely reactive. So that's, so when you get the information, okay, from the sensor to your agent, and agent is sending some kind of actions, okay, some kind of signals, and then we call it a purely reactive agent. Okay, a thermoset is a purely reactive agent. See, now someone was asking what is reactive. That is perfect example. Thermoset, right? Doesn't depend on anyone. It has a sensor to sense the control, and then it's going to change, right? Whether whatever the temperature you are setting up, 20 degrees centigrade, 22, 24, whatever your comfort level is, right? So you set it, and then thermoset is going to perfect example of purely reactive agent. Perfect example. Now, reactive architecture. There are many unsolved problems associated with symbolic AI. Okay, now I think it started solving a little bit, is coming, but it's not solved that normal human being can use it. Means probably in the company level, but not at the in the hands of a normal person, basically. Okay, these problems have led some researchers to question the viability of the whole paradigm, okay, and to the development of reactive architecture. Although united by a belief that the assumptions underpinning mainstream AI are in some sense wrong, okay, reactive agent researchers use many different techniques. Okay, so again, controversy, I would say. Okay, but in recent last couple of years, AI is being more popular and solving some of the unsolved problem. And I already gave you the example of that Alexa, right? Just unimaginable. Now you have a teacher sitting in your house and telling our kids, basically, okay, means I don't have to spend time with my kids just teaching them 1 + 1 and 2 + 2, right? And asking some simple questions. No, I like to do that, but I'm just saying that if they can learn by doing that with interacting with the Alexa, that is a good time use. If I can spend that time to do something constructive, that would be good time use for the family, right? And then for the country. So it's very important, those kind of development. Limitations of reactive agents. Agents without environment models must have sufficient information available from local environment. Generally speaking, agent will never have full information of any system. Okay, that is just beyond. And I would say it's just not the definition, right? Definition is very simple. Little intelligence with local information, okay, and some kind of actions, okay. So if decisions are based on local environment, how does it take into account non-local information, right? That's where the multi-agent comes in, okay. So you have a local information, you can do something locally, and that is why that agent is being built. How you can now use that and help other agents so that system-wide meaningful actions can be performed, okay, or some system-wide information can be achieved. Difficult to make reactive agents that learn, okay. What is difficult? Learning in agents, okay, that is recently probably might have started because of AI, but 5 years back, there was no such paper that talks about agent has a learning and helping that learning to solve power system problem. Okay, there was no. So if you are a PhD student and if you are trying to do some kind of decentralized control, learning is a new thing. If you add learning in the agents, okay, some kind of learning, okay, learning means utilizing the past data, okay, and come up finding that one and utilize with the current information. That's the learning means. Okay. So learning is not present and widely, at least on the power system areas. Okay. So difficult to make reactive agents that learn. Okay. Since behavior emerges from component interactions plus environment, it is hard to see how to engineer specific agents. Okay. Since behavior emerges from component interactions plus environment, right? It is hard to see how to engineer specific agents. No principal methodologies exist. It means it's system specific, basically. Okay, system specific, not is set methodologies. But there are set steps that you generally recommended, but there is no set methodologies that you and it depends on definitely system as well, right? It means what you want to achieve from that, doing that. So it is hard to engineer agents with large numbers of behavior. Okay, remember, behavior is just a function in a software program. Okay, but behavior, the word behavior is because you are going to repeat it and repeat it. Okay, so it is hard to engineer agents with large number of behavior, because when we talk about agents, we talk about kind of relating that to the human perspective as well, right? So everyone has a behavior, right? You individual, right? Every person has a different behavior. So agent has a different behavior, right? So dynamics of interactions become too complex to understand. Okay. It is hard to engineer agents with large numbers of behavior. Okay. And if you do that, then making any changes are very, very difficult for another person. Very difficult, right? Probably if you build a system, let's say, for any power grid, any electric utility, maybe let's say monitoring one whole grid for one city, right? If you build it, if you put a lot of efforts, you understand every detail of it, okay, and you build it, right? But after 5 years, it's still in operation, and after 5 years, if someone wants to make any changes, if it is just one agent, okay, that's gonna be extremely big. And I guarantee from now only, I can say that whoever is going to make the changes is going to break something, okay, unless it is properly documented. And even if it is properly documented, every single behavior or every single method that you build is just unimaginable to conceive for one individual. Probably if you build it, maybe 10 more engineers is needed to just understand and make any changes in that particular software. So it's very important, large behavior. Okay, so when your system changes, you have to make changes on the existing infrastructure, existing software, existing controls, right? Very important. Limitations. So these are the limitations that we have. Cognitive agents, also called deliberative agents, possess an explicit knowledge of their environment. Okay, so cognitive agent we are also calling is deliberative agents. Okay, it has knowledge of the environment, it has the knowledge of the power system, it has the knowledge of wherever it is, what is the load probably, okay, what is the switch status on off, okay, whom to communicate, okay, and if something some information is received, what to do with that information, okay, what actions are needed. So it's kind of deliberative agents. They use sophisticated knowledge representations, have expertise, goals and plans. Okay, so knowledge representations they have, expertise, okay, goals and plans. Cognitive agents have. They must interact and engage in cooperation with other agents. Okay, definitely without engaging with other agents, we don't have the multi-agent system. Okay, it can be used for solving problems too large to be solved by a single agent. That is, one problem is restoration. One agent cannot. And restoration is currently means in 1995, I think I'm going ahead on what my plan. But in 1995, restoration problem in the United States thought that it is solved. Okay, and when you say, if I say you have a switch, one switch that is open and closed, right? You can say, yes, I can solve it. If I say I have two switch, you can say 4 combinations, right? 0, 0, 0, 1, 1, 0, 1, 1, we can solve it. If I say 4 states, then probably you say, okay, 2 to the power 4, 16 combinations, probably I can solve. And now think about, we have thousands of switches. Okay, so as soon as if our 2 to the power goes beyond 10 or 12, then things will be messy. Okay, things will get complicated. The computation power is not sufficient to solve this one. Okay, so then probably these kinds of agents can help us, right? But still, it's just think about the problem. 2 to the power, we have 10 switches. Just think that number is, or if you have, we will not have 10 switches, right? If you are talking about in the substations, right? We have in substation itself, we have 10, 20 switches. So when you have multiple substations, then you have multiple switches, right? So just very large problem, restoration problem. Okay. So anything, even something we can do about it. Okay, that is good thing about the restoration problem. So addressing naturally distributed problems. Okay, building modular systems. So this is where we can use cognitive agents. Okay. Okay, hybrid agents. A pure reactive architecture is not enough to ensure a consistent permanent behavior in agents. Not enough, it is saying. Okay, pure reactive architecture is not enough to ensure a consistent permanent behavior in agent. Okay, introducing goals and goal directed behavior into reactive agents. Okay, introducing goals and goal directed behavior into reactive agents. Okay, are needed basically. Interface agents. Again, every multi-agent system, there are a couple of multi-agent systems out there. Okay, but every multi-agent system have this kind of agents, right? Without that, we won't be able to basically build multi-agent system. It facilitates the interaction between a user and a computer. Interfaces, user and a computer, right? Improve interaction. Example, accessing information, assisting with current work. Okay, doing learning or just providing entertainment. Okay, improve interaction. What are the main characteristics of these interface agents? Agency, responsiveness, competence, and accessibility. Allowing them to appear understanding, helpful, and competent. Okay, that's one characteristic. Allowing communication in tune with the users. Okay, that is another. Responsiveness. Okay, that is another characteristic. Yes, Goel. Yeah, Jade, and there are one couple of more. Yeah. Competence, having meta information about subject to be addressed, right? Competence, right? That's called competencies. Meta information about subject to be addressed. If you are going and speaking in any way, anywhere you are speaking, that means you are competent because you have some information, then only you can speak, right? And if you speak without information, meta information, then kind of they will say you are speaking out of bound. I don't know what you are speaking, right? So it's competence. These agents are competent. They have some information already, and then they are trying to do something about it. Okay, and they are trying to address something about it. Okay, with that information. Accessibility, by providing an adequate physical interface. Okay, adequate, because it's saying connecting user to the computer, right? Interaction between user and computer system. Interface agents. Middle agents or intermediate agents. Okay, remember what we are talking about in general. Okay, so when you build, you do not need to have every single agent, right? That we talked about: software agent, reactive agent, hybrid agent, and all other agent, interface agents, right? You don't need every single agent. Probably you may need 1 or 2 agents, okay, to build for our power system. Okay, whatever the purpose, there are lots and lots of applications that the researchers have used to solve some power system problem in using this multi-agent system. Okay. Middle agents or intermediate agents. Okay? They are internal agents which play a particular role providing intermediate services. Okay. They are internal agents which play a particular role providing intermediate. Middle agent, right? Means we know the name middle agent means, right? He's the middleman. That's what it is, middle agents. Okay. But what is the perspective of the power grid? What are the middle agents on the power grid, right? So if you have a, let's say, generation, transmission, and distribution company, so anyone that is communicating between these entities, then we can call that agents are the middle agents, right? Because we need these interfaces, right? Without generation, if you only have generation, there is no system. If you have only transmission system, there is no. We need all three to make the power grid work, right? So they are internal agents which play a particular role providing intermediate services. Role: provide yellow pages service to dealing with the intricacies of high-level protocols for matching a request to a particular service. Okay, intermediate agents. Okay, so a simple example is if you build a system, okay, and in that system for power system, let's say one agent is responsible for getting the data from the SCADA. One agent responsible for analyzing the data, right? One agent is responsible for acting on that analysis. So now you have these three different agents, okay? And so all are doing, and then this all the agents, what they are doing, and that agent information is given to somebody. Let's say we call it intermediate. So intermediate agent knows that agent 1 is doing this, agent 2 is analyzing the SCADA data, agent 3 is acting on that data, that information, right? So that is kind of a broker you can think of here is a, or controllers, facilitator, mediators, or matchmaker. Okay, so that's the role of this intermediate agent: broker, controller, facilitator. I would say facilitator. Okay, what is the difference between intermediate and interfacing agent? Intermediates are this. So I think probably you can understand, Monica, right? These are all intermediate agents, okay? And what are interface agents, okay? So facilitate the interaction between user and computer system. That's our interface agent. So computer system, and then when we are talking about here, this is all computer here. Okay, there is no user here. So user and a computer, basically. So that's the interface agent. So interfacing with the power system. Okay, so maybe taking user, because user is requesting some information. Let's say, I'm thinking. Okay, so user is, let's say I have an outage in the system. Okay, and now user is requesting that I want to, what are my options? Okay, so then interface, so interface agent is now interfacing user to the computer system. Okay, and then say these are the, so it is sending that do this my restorations of this ones, okay, on this one. And then once you have this one, now you have all the roles of this, okay. So then user is requesting, now this agent started working on it to restore the system, okay. So all the agents that you have now is going to this intermediate agents, okay, and seeing what are the roles of this, how they are communicating with each other, what services they are going to provide, so that I can achieve the task that is being requested by the user. I hope that help, Monica. Okay. Okay. Desirable characteristics of an agent. Okay. So network centric, distributed, and self-organizing. Okay, distributed and self-organizing. Those are the desirable characteristics. Again, this is basically theory that we are working on the agents. We don't need every single item that we are talking about, but just a general information. What are agents? Why the agents are important? Because so much out there for the agents. Okay, that is why it is important. Okay. Network centric, distributed, and self-organizing. Then communicative, able to interact with other agents through communication. Okay. Semi-autonomous, neither always under the control of humans or other agents, nor completely autonomous. Meaning humans should be able to control the amount of agent autonomy, right? Humans. But generally, we want agent to be autonomous. That is why we are, for power system application, we want that agents to be autonomous. Okay. But at the same time, means if we want to stop it, right? We should be able to stop it. Reactive, react timely and appropriately to unforeseen events and to changes in its environment. Reactive definitely means, we talked about several times. Reactive is for anything that we do with the agent for us applications. Okay, that's the reactive. So reactive part definitely will be there for us. Okay, reactive will be there. Coordination part will be there. Okay, acting on the environment, that is the reactive part. Okay, and collaborating, coordinating, distributed, right? Those are the things that we will have in our agents in power system. Okay. Other desirable characteristics of agents: deliberative, capable of sufficient deliberation to perform tasks in a goal-directed manner. Okay, goal-directed manner is very important, right? Either you are trying to restore the voltages, okay, or control the voltages of the system. Restoration, I have given many examples now. Maybe you are doing power market, right? How you can do that? Power market, selling and selling generation, if it is generation, selling and receiving contracts for power transfer, right? Similarly, for the transmission company, how much power is going to flow through that transmission? What will happen if it goes beyond the capability? It's not like that we have switches that exist, that if power flow goes beyond this, then just turn off my breakers, right? Means there will be some kind of overloading we expect, and we do it, means all the time, 5% or whatever the rating of the transmission lines. Okay, so deliberations are very important. Collaborative characteristics of agents: interact with human and other agents. Collaborative interactions allow agents to resolve conflicts and inconsistency in information. Current tasks, thus improving their decision support capabilities. Okay, collaboration is very important. Without collaborations, you won't be able to achieve anything. Basically, you have to collaborate, okay, with other agents to achieve something. Okay. Dr. Prerna is requesting something. Okay, just a second. Do you see my screen? Do you see presentation or do you see my browser? 8:40 p.m. IST to EST. Okay, 11:10. Okay, we can do that, Dr. Prerna. Okay. Yeah, 11:10 a.m. we can finish it. Okay. Sorry, I just saw your message, Dr. Prerna. Okay. Okay, sorry. Collaborative, right? I was talking about collaborative characteristics are important. Proactive, right? Capable of taking the initiative, not driven only by the events, but capable of generating goals and acting rationally to achieve them. Recognizing opportunities, so many things, right? Once you have the data, you can come up with so many things that you can do, right? Just like a human being. If you are a substation engineer, if you are working in a substation, or if you are working in a control center, or if you are a developer, means manufacturer somewhere, working in transformer manufacturing facility, transmission line manufacturing, what you see, okay, and what you act, that exactly means what it is. Okay, can we prevent? Okay, something is going to happen. We know that it's going to happen, right? Can we prevent? Proactive, right? Or kind of predictive, we can say that also. So proactive, collaborative, deliberative, right? Network centric, okay? Communicative, semi-autonomous, reactive. Those are the characteristics that we know that agent can have, right? Okay. Desirable characteristics of an agent. Okay, that's done. Sorry. They are more predictive, able to make predictions about the future. Okay, and that is kind of learning, right? Means if you predict, that means you learn something and you are predictive, right? If you have a predictive behavior inside your agent, that is something new, probably, I would say, if we do it. Okay, if you do it in your master's or PhD work. Adaptive, accommodate changing user needs and task environment. Okay, adaptive means accommodate changing user needs and task environment. Persistence, capable of long periods of unattended operation, right? I mean, that's what we are looking for. Anytime when we build, we want that system should last forever, right? Means generally that's the intention, but it's not, right? I mean, because things are changing. When your environment changes, you have to change your old algorithm, your legacy system. Okay, you have probably heard many times legacy system. Okay, what is legacy system? Okay, anything that is working, that is called legacy system. Okay, anything that is working for several years. Okay, so any like software, okay, legacy system. Okay, any system, you bring it in your control center and you install it. So then now that will be your legacy system because it's working. We install it, we put a lot of efforts. Okay, and so it's changing legacy system. Okay, that is definitely gonna be needed when things are changing around us. Okay, persistent, capable of long periods of unattended operation. Okay, mobile, able to move around network if necessary. Okay, that is, we already discussed that. Okay, now those are the characteristics. Now modules. Okay, what modules agent can have? Okay, or agent needs, basically. Communication interface, definitely, right? Without that, he's not going to receive or send information. So communication interface are must. Only interface to other agents. Okay, that's the things that we need. Okay, implemented using methods or functions. Okay, technically only interface to other agents, kind of not 100%, because we have to have some kind of yeah, I think only interface to other agents. Okay, we'll talk about it. Implemented using methods or functions, right? Basic module. Processing of messages requires following steps. Okay, processing of messages requires following steps. Receiving, storing, and sorting messages. Okay, receiving, storing, and sorting messages. Without that, we cannot build agent. We need to receive the message. We should be able to sort the message. We should be able to store the message and sort it, right? Decoding message content for further processing. Okay, message content. So we should be able to decode the message, right? If we receive the message and that message language is different and we can't understand, then what is the meaning of the message, right? So we should be able to send that message, right? Means if you are means it's understandable. If someone is going to send you a message in different language, you are not going to understand if you have not used that language before. Very simple, right? So similarly for that one also, for our message, when we receive it, we should be able to decode it. Okay, generally any communication, right? So any communication, there are protocols in power grid equipment. Any communication, if you want to send a message, means send some kind of signal, right? Data signal. So there is a protocol, power line carrier, right? If you have heard about it, so that there are protocols in this. So when you are receiving the message, you know exactly what bit is what, okay, what information contains on this one. So every single in any phasor measurement units, when they are communicating, so there are protocols like if you have run power flow and if you have used MAT power. Okay, if you have not used it, you should go and check it out. MAT power, so there are files, model, power grid model. So there are standards. What should be the first row? What should be the, okay, Santanu Srivastava, you are writing something on my screen. Santanu. Yeah, I think probably we need to disable that feature on that one. Okay, probably next class. Probably work for Dr. Prerna. And but that's okay. She is very accommodating. She worked very hard on this one and collaborated with us. So okay, so sorry, I deviated a little bit from what we were talking. Okay, so receiving, storing, and sorting, very important. Messaging, decoding messaging. Okay, outgoing messages requires encoding of the information to be transmitted. Right, we don't want that everyone should be able to read our message. Right, so it should be decoded, and WhatsApp is the perfect example. Okay, so whatever you send or receive, that is decoded before sending and receiving after. You receive the message after decoding, so no one else can see it, okay, except the WhatsApp builder, means the developer. They can see everything, but general public we can't. Okay, no one can decode it, means anyone, even hackers cannot decode it. Okay, so the decoding, outgoing messages requires encoding of the information to be transmitted. Right, when we are sending that, if we see a fault, right, and or if we see that voltage problem in the generator controller is not working properly, so we don't want that information to be out, right, because there is a market, someone can take advantage of that information, and we will have a price hike. We even don't want to share that we have a peak demand, right, or low demand, those kind of information. When it is available in a public domain, then traders will take advantage of that information and deliberately change the price. Okay, deliberately change the price, though the price would be X amount, then they will change it to X plus Y amount. Okay, so that's those information. Network topology, right, that is also a big deal now because of this cyber attacks. Lot of things has been done in the United States to remove that information from the net. Okay, so now if you see in the Google, some of the electric grid network that was very, very visible earlier days, now those Google somehow manage to understand that that is a image of the electric grid and low resolution images that you now get. Okay, so a lot of things are happening on that. So that is very important. Decoding is very important. Mailing it to according to the exchange protocol. That's what it is, right? Mailing it according to exchange protocol means very simple. Probably sending a letter, right, where you should write your address, where you should write the receiver's address, right, sender address, and those kind of things. These are the protocols, right? So we have to have, when we build a system as a multi-agent, we have to have this kind of professional. As a student, you can build whatever you want, right? As far as it works, you have the theory, and you executed all the behaviors, all the algorithms in a meaningful manner, and it works for at least one or two system. Okay, at least one system or two system, and any changes in the topology, then I would consider that you have done a good job. Okay, and your software is good enough. But when it is in the professional, then all these things that should be incorporated, because now you are doing for the professional, right? Somebody's life, somebody's money, right? Funds are at stakes when we as an engineer makes this kind of error, right, unknowingly. Okay. Basic modules for an agent. Okay. Perception, interface to its environment. Okay. Obtain signals from the agent's sensors and may also receive messages from other agents. Sorry. Okay. Obtain signals from the other agent's sensors and may also receive messages from other agents. What is perception? Right? Perception system, we call it. So this is an environment. For us, environment is the for us environment is power grid, right? Power system. And then agent has see function and action function, right? So agent sees our environment and act on it, okay? Action means closing the switch, changing the set point, okay? Providing any information that is needed for our controllers, okay? Anything, okay? I see a message from Srikant. Do the exchange protocols with agent-based system make system less transparent and more costly? From the user perspective, these exchange protocols, Srikant, at least from the multi-agent perspective I am talking about, is we want to take a multi-agent system that has already built-in exchange protocols. So we should, as a power engineer, we should be not be spending time to building exchange protocol, because anyway, it's not our job, right? It doesn't come. We cannot build actually. We don't have the qualification to build the exchange protocol, right? It's a computer science or computer engineering job to build that kind of exchange protocol on this one, okay? But what needs to be what information and we will be exchanging, right? Voltage, current, power, or whatever that we have to provide this one, right? But exchange protocol is generally coming from the system, whatever the software that we are going to use it this one, okay? So yes, means it will have some kind of overhead, right? Because now you have to do additional work, right? Before sending it, you have to encode it, and after receiving it, we have to again decode it, right? So definitely that will play a role on that one, yeah. But it is for sure for the power system, we don't want it to be transparent, right? I mean, we don't want that it should be seen by anybody, even if someone hack into our messaging system, that person should not be able to understand, okay? Normal person, okay? But generally, as a power engineer, if you are putting efforts with some kind of a very important transmission line and very important generator, right? Very important, you know that this is a critical. And if you tap into that somehow, if you get access to that one, and if you tap into and study for days and months, probably you should be able to figure out, because it's not hard, right? It means once you know that, okay, these are the digits, so you should be able to figure out. But it's not intuitive, means it's not someone can do it in 1 day or 2 day or 1 week, means that is what. So we want to hide our communication. We don't want to be we don't want anyone to be seen, anyone to see those communications for sure. Hope that helps, Srikant. Okay. The C function is the agent's ability to observe its environment, whereas the action function represents the agent's decision making, right? C and action, very simple. We already saw that, right? Agent sees the environment, okay? Means receive the information from the environment, work on that information, and then based on the information and based on the behavior that you have built it or method that you have programmed it, and then agent will do the action. Or action can be anything, right? Action can be simply pass that message to another agent, okay? Action can be send a control signal, okay? Action can be sending to everyone, right? Message, sending an action. Those are the two actions that I am thinking, right? So you can send it, okay, to another agent, or you can send a control signal. So execution, basic module, execution. So what we got so far, okay, different interfaces, okay, and then perception systems, perception, little bit detail talked about, and then this one is execution. Significant event has occurred, take action. Okay, significant event has occurred, take action. Very simple, right? Action could be no further action, or to take or send message to another agent to take an action. Right? Very simple. Social knowledge, to interact with other agents. Okay, that I am healthy. Basically, think about that. I am healthy. I am monitoring, just sending to your interface agent, okay, or broker agent or facilitator, that I am available every couple of minutes, okay? Said, okay, I am here, I am monitoring, I am doing my job, okay? Or to your neighboring agent. Communication, knowledge about the means of inter-agent communication. Example, information about communication channels, location of agents, language of communication, right? 3 things: communication channels, location of agents. What is location of agents? Well, basically, if it is just a one computer, what is the port it is listening, okay, what is the port that is sending. If it is multiple computer, that we have multiple agents at different computer, then what is the address and what is the port number, right? That is what generally the case. Okay, again, it's not, we don't want to deal with that. That's the computer science, okay? But generally speaking, what is the location for us is, like, it's not the location is West Virginia. Location is generally the IP address and the port number, okay? Interaction, how to interact with other agents in order to procure services. Right? Means if you are looking for something, how you can find it out, right? Very human, right? If something goes wrong in our house, right? How we can find out? That's exactly same thing we want to program it. You think about as a power system. Something goes wrong, what needs to be done? What agent should do, right? If there is a load agent, okay, if we have a load agent and we see that load doesn't have a voltage, okay, so just think about as our house, and when we don't have the house, what we are going to do? What we are going to first thing, tell me, okay? We are going to say, I will just go out and see my neighbor has a power or not, and that's the first thing. Same thing here, okay? So when we say that that load agent is seeing no voltage, is going to send a message to another load agent or whoever is the neighbor is, right? And said, are you still, you also see the same? I don't have the voltage. And then probably, okay, I think we should be okay, maybe half an hour. We should just wait and the light will come on, right? Or we can say, okay, probably we should call the utility company, okay, and see what's going on. And generally, if you call, if it is a planned outage, you will hear a message, at least in the US, okay, you will hear that we know there is a problem, we are working on it, and then it will be resolved in 30 minutes. So generally, that is the message we get. Okay? And if it is outage, they don't know it, they will say, okay, where is the address, everything they will use. So that's exactly what we are talking about, interactions, how we are interacting to find the information, to get the power. So very same interactions we should be. So when we do that one, that will save everybody's time, and we can find out the problem quickly, we can fix the problem quickly, and so many other things we can do on this one, okay? Interaction. So agent models, okay? Use these models to identify other agents with whom it is useful to interact and to make this interaction more effective, okay? I already gave the example, okay? Interacting. Without interactions, you won't be able to find out what is the problem, right? So use these models, agent models, to identify other agents, right, with whom it is useful to interact. And to make this interaction more effective. So we don't want that generator agent should be contacting, the load agent, right? We don't want that, right? Generation, we know that generator is going to send power to the transmission line. So that communication should be between them. We don't want that generator should be talking to, means that is unnecessary, right? Similarly, load agent, we don't want load, means like user, right? Us, we don't want be calling to the generator company, right? Means we just not need it, right? In some sense, in some probably sense, if we are talking about microgrid, probably yes. Okay. Okay. So self-knowledge. Okay. So knowledge about itself. So when we build an agent, what is the self-knowledge needed, right? So physical state, location, and skills. What skills do I have? Okay. What is my role, right? Where I am located, who is my neighbor, okay? Whom I need to contact when I see some actions that I have to perform, okay? What actions I have to perform. So self-knowledge is very important to participate in task and reply to other agents, okay? To participate in task and reply to other agents, very important, self-knowledge, okay? So which task I have to participate, which agent I have to reply to, okay? So because now there are lots and lots of agents, every agent is sending a message to other agents. So do I really need to, like I already gave example for generator agent, if generator agent is sending me a message, do I really need to reply? Probably not, right? So means you need to know whom I should. So generally neighbors are the most important one. If you are neighbors, so that information should be known, self-knowledge, okay? And then learning. Learning is, again, I said, new things in the agents, okay? to adapt is changing environment. Right? When we build a system 10 years down the road, okay, nobody knows, right? But as a best educated, experienced power engineers, okay, what best we can think of, okay, what is going to happen, okay? Maybe we know that definitely 7% load is going to increase or 10% load is going to increase, okay? Maybe we have additional feeders, additional lines coming in here, okay? So the intuitive things, if we can add it, okay, then we can say that the agent is adapting to its environment. Yeah, very important. When we write, currently we are working on a proposal for the state, okay, that is about a $2 million proposal. That is 2 million is 20 lakhs, right? So $2 million proposal that we are writing. So in that one, the first question when we had a meeting is that, what is our current state? Okay, at this, what is the status of the grid in West Virginia? Okay, that is the question. Okay, now if we don't know this one, then there is no meaning of writing proposal, right? So we have to figure out. If you don't know it, then we have to figure it out, right? And then what will happen in next 10 years, right? Where things are heading, right? Now, every single person, if you meet in conference, that we are heading towards 100% renewable grids. That's where we are heading, okay? And if you ask, is it possible? Okay, depends, right? Whom you are asking. Okay, but if knowledgeable person who really worked on it, who have seen the problems of renewables, probably say, probably very hard, okay. Is it doable? Can we have 100% grid? Probably yes, right? If is a scientist, right? If it's like us, faculty, yes, why not, right? As an academician, we will say, why not? We can have it, okay? So different people will respond differently, okay? But that's where we are heading, right? So what is the missing? Now we know where we are heading, where we are right now, what are the missing steps, right? If we can put everything together, then we have a very strong proposal, right? So similarly here also, when we are building system, if we know the obvious things, right? If we can add it into it, okay? And probably a flag, and if this will happen, you do this couple of, then we don't have to replace the whole legacy system. Okay, we can just tweak it. Okay, we can go to, because we have already thought of this. We have thought of 10 things that can happen, and out of 10, 2 happen, and then our system, we don't need to change anything. We just change. Okay, instead of A method, now you need to use B method. Okay, so it's possible. I mean, learning, that's called. Okay, prediction. Okay, decision making. It is very important module, right? Decision, that's what decision making. Action is, okay? Action is decision making. So you see and act, okay? See and act, decision making. It is very important module. Very simple to very complex agents needs this module for making decision according to its knowledge, right? Whether it's sending a message when you see a low voltage, when you don't see a message, that's the decision that agent has to make. If I am not seeing a voltage that I'm accustomed to see every day, right? Every single time that I'm getting the data, and I'm not seeing, or unusual, different than what I am seeing, what is my action, right? Where I need to communicate. So that's the decision. So I need to communicate when I do not have a voltage. That's the agent job, right? If you have a program for that particular job, okay? So now I don't have the voltage, I am communicating with my neighboring agent. That's decision that agent made, that I am communicating, okay? Control. For controlling the information flow, okay? Mapping of agent's goal into operational actions and monitoring the execution action, right? Control for controlling the information flow, mapping of agent's goal into operational actions and monitoring the execution action, right? So basically controlling, okay, the flow of information, whom to contact, where to contact, what actions to take, Okay, so those comes into this one, decision making and control are together, I would say it. Okay. Okay, so I think let's see what we have. So I think we are going into the next realm. Okay, that is now we have enough. So what I gave today is the enough understanding of the overview of the power grid. Okay, and then what is happening with the energy management system, where agents are missing. Okay, and what is agent, what agent should entail basically. Okay, how agents should look like, what they should possess. Okay, those are the information that I delivered today. Okay, so now next is that we will be seeing applications of agents on power system, what researchers have done, how they have used this agent system to do what. Okay, that's the next topic. So I think this is a good place that we should stop today. Dr. Prerna said 11:10, but I think 11:03. But let's have a couple of questions. If we have a couple of questions, then we can go to 8:45 p.m. Sorry. Okay, so 8:45. My time is 11:03. Okay. So, R. Goyal, I don't know what is your first name, Mr. Goyal or Miss Goyal, I don't know. No, but I think I will be showing you how to run the JADE, okay, and probably an example how to communicate. Okay, so I think that will help definitely, and at least point out where you should be looking at it for documentation, and then you should be able to do it. Okay, so. Swati, we are not going to probably doing different episodes, but we will talk about this in agent applications, and probably see some of these. We will, like I said, that each multi-agent system is unique for that purpose, right? Each unique multi-agent system, what is the purpose? So that is the next topic. So probably you will see a lot of examples, and it will help, Swati. Okay. Can you please tell what software we need to install in advance? Nothing right now. Okay, Srikant, but if you have a MATLAB, that would be good. Okay, if you have a MATLAB, that would be good. So yeah, nothing. We are not. I will just show you probably, and then you can do the installations. Okay, Srikant. So I will show you the JADE and a little bit small example. So I have the old setup, not the new one. So probably at least I will point out that these are the differences, and probably you need to work on this side to make it happen. The learning time is a lot. Okay, but if you are doing masters and PhD, that's perfect opportunity to spend time, your time worthwhile to build something. Okay, any other questions? If you don't have the question, okay, so probably so we already talked about is Sailendra. What is the AI and agent? AI is like a whole system we are talking about. An agent is like local information in the local environment, what it is doing. And always when we are talking about agent, is not just independent. We are talking about multiple agents, how they are interacting. Okay, so agent is not an AI, or AI is not an agent. Okay, I would say AI is not an agent. But if you say that I am just building one agent that is just going to do load forecasting, and if you in load forecasting you are using reinforcement learning or all AI algorithms, then probably that agent we can call it an AI agent, right? Because you have the AI methods, and that agent is just doing one task, that is load forecasting. Okay, so it depends on how you are using it. But general sense that agents are cooperative, like we said, okay, and coordinating with other agents, receiving some information from other agents, and acting on it. Okay, versus AI is like holistic pictures. It has past information. You train the AI. In agents, we don't train the AI agents. We don't train it. Okay, but if we put a little bit learning, probably, yes, we are adding some component of AI onto it. Shailendra, hope that helps. Okay, any other questions? I can't see the video screen, so I don't know. But okay, I don't see the background. I don't see anyone's name. So yeah, probably I request Dr. Prerna to keep that video screen on. Means that way I can probably, I feel more like attached to
Yeah,
you guys.
video screen is on. I think I can request all the participants to on their
No,
camera.
we don't want to on. We don't miss. But I am not able to see the screen. Even like generally you see the name and no photograph, right? Yeah, that's this screen I am not able to see. Now I see it. Yeah. So I don't know why it was, but I think, yeah. So now I can see that. Okay. Probably. Okay. So that's good. Any other questions? Probably see, I say Srikant is asking questions. That's good. Okay. So if you are not asking questions, then it won't be helpful. Otherwise, I will just talk it out and then we will be done. Remember, the goal is that you can get best out of it. Okay. And not generally the how to, but instead of concept wise, right? That's the goal here, right? How to is generally the students' work. I mean, exactly how to do it. Dr. Jignesh, tell me how to do it. Means how to do it. Generally, my student has done it. This one. Okay, so I can give you overview, my perspective, and whether it is a good thing to do based on my experience. Those are the things are generally more meaningful. Then how to you can generally, if you are asking right question, you should be able to find it very with less efforts how to, because YouTubes are there, Googles are there. If you consistently search for 1 or 2 weeks, and even if Google is not bringing that, but after 2 weeks is working hard on the behind in scene, because they know, Google knows that when you requested some information, it produced only 100 results. So now he has to find why I could just give 100 results in the world. So now their agents, Google program is going to search all available resources to find it. And then when you again come back for maybe 1 week or 2 weeks, probably you will see instead of 100,000 results or 100,000 results, those kind of things. So just you have to be patient with Google that, oh, you couldn't find it. But no, it's there. Google needs time, because Google was not expecting that Ravi or Dr. Prerna or Dr. Jignesh is going to search this information at this location at this time. Okay, so have a good night, have a good, what you call, a good dinner, a good time with your family. If you are a student, chill a little bit, half an hour, okay, and see what has been taught,
Yeah,
okay?
thank you. Many thanks to Dr. Jignesh. Now I
Okay then.
request all of you to please put on your camera so that we can take a screenshot.
Right.
It is required for our because this lecture is being recorded. So all of you are requested to please put on your cameras so that we can take a screenshot. And I request Ashish to take the screenshot from MNIT.
Okay, ma'am.
Please put on your camera, everyone. Are you not able to? Because I cannot see the people. My PC doesn't have webcam, ma'am. So
Shivam, Vivek, Pavitra, Ashish, Vaibhav, Shiva Sankari, Krishna, Revati, please turn on your, yeah. We would love to see you guys, yeah. I hope you are learning something.
but why their videos are not visible?
Yeah.
Am I visible to all?
Yes, Dr. Prerna, I can see your face. Yeah.
Mhm. So what about the others? How will we
Ro-
take the screenshot then? I think
Rohit,
Dr.
you are
Jignesh,
asking some question. What's going on, Rohit?
where is Dr. Rohit? Yeah, Dr. Rohit is also there. Dr. Rohit,
Oh,
please put on your camera.
sorry,
Uh,
I did not know that this is Dr. Rohit. Dr. Rohit Kumar. Okay, so it's raising hand. Probably might have clicked it. Okay, I thought. Okay, that's okay.
okay, now Dr. Jignesh, I think you should first. I think you should stop sharing the screen.
Okay.
Then only I think
Okay.
admin disabled the video. Okay, the people are, but I did not. I did not. People are visible. So, Ashish, let us have this kind of.
Yes, ma'am. I've taken the
Yeah,
screenshots.
but only such less number of students. How can we? Yeah, this is the gallery. Yes. So this is one screenshot we can have. Let us have the another. Take the screenshot, Ashish, please.
Yes, ma'am. Yes, ma'am. Done, ma'am.
And then we have the third one. This is the fourth one. I hope Dr. Jignesh, you can also see the people.
Yes, yes.
Fourth one. This is the fifth one. Sixth, people are not there. Seventh. Ma'am, I'm not able to turn on the cam, Rohit Kumar. So why are you not able to? I don't know. Are you able to do now, Rohit Kumar? So I don't know, but yes, most of them have been able to. So thank you, everyone, and let us meet tomorrow at 5 p.m. again. Thank you, Dr. Jignesh, for your time and effort.
Thank you, Dr. Prerna. I think that was a great lecture today. Okay, and thank you for the inauguration ceremony. Thank you to everyone who was involved for organizing. I think I am enjoying, and I am sure students are enjoying. And if they are not, they should enjoy it and take full advantage of this 5 days lecture series and learn and ask questions. Very important. Thank you very much.
Thank you, sir.
Bye.
Thank you. Thank you. Bye. Bye. Bye, all of you.
Bye, guys.
I'm ending.